Stop watching AI news and start building the tech behind it. In this crash course, we are going from a blank notebook to a fully trained text classification model using the exact Hugging Face workflow used by professional AI engineers. We are skipping through the noise to focus on the technical core, building high-performance data pipelines, mastering tokenization, and using transfer learning to make your models smarter. To guide you through this, we brought in one of the most loved machine learning and AI instructors online, Daniel Burke. If you've seen Dan's work before, you know his energy is just on another level. He has a real gift for taking technical machine learning concepts and making them feel like common sense. By the end of this video, you'll have a professional working model in your hands. Now, before I hand it over to Dan, we have an extra special gift for you. We're opening up our private Zero to Mastery Discord community for free, but only for a limited time. You can get help from our mentors, ZTM instructors, including Dan, and work alongside thousands of others in the community. You can get the invite link in the description down below. Make sure to grab that before it expires. You ready to get started? Let me hand it over to Dan. Enjoy.
Hello everyone, and welcome to the Hugging Face Bootcamp. Woohoo! Look how happy that guy is. That's how I feel right now. And so you might be asking, what is Hugging Face? And well, a formal definition would be an open source powered ecosystem for machine learning and AI, but I like to think of it as the homepage for AI. And let's go have a look at it, hey? Here's my profile, Mr. D. Burke, and you're going to notice a recurring theme as I go through a few different profiles. We've got spaces, which are demo applications you can share. Models, which are trained AI models or machine learning models that you can train and share with other people. And data sets. Of course, all of these are public right now, but you can create private applications, models, and data sets as well. And that's what actually I do for a lot of clients that I work with. If I'm training a model for them, I'll put it up here and share it with them and only them. But what I do most days is come to the Hugging Face models page and see what open source models are available. These are models that I can download or you can download and use it on your own computer for whatever use case you want. And then if we go here, OpenAI have their own page. They've got models, spaces, and data sets. You're going to notice this is a recurring theme. Spaces are applications, models are trained model weights that you can use to infer on data, and data sets are data sets that are often used to train or evaluate models. And then we've got Apple, data sets, models, spaces, Google. We go down the same thing, spaces, models, data sets, Facebook. You get the theme here, spaces, models, data sets. We're actually going to use that as our motto for the course, but we'll see that very shortly. And then we can even try out models. So this is a Qwen 3 VL 8B Instruct, a bit of a mouthful, a model from Qwen, and it's Apache 2.0, which means it's open source. We can use it. And it's a VLM, which means it's a vision language model. We're going to get hands-on with one of these later on in the course, but if we go describe this image. So what a VLM means is that it can see pixels as well as just text. So there we go. It can describe our workflow slide. We'll get hands-on with that shortly. And I want to introduce you to one of the main resources of the whole course, and that's the learnhuggingface.com book. And so this is going to have all of our course materials from text, code, links, you name it, it'll all be here. So if we go into one of the demo projects, these projects are end-to-end. We start with a data set, we train a model, we build a demo. So that's what we looked at before, data sets, model, spaces. And so this demo is going to be publicly accessible. So if we just click the link here, there's the Trashify demo. We're going to work towards that in the object detection project. So if we go back to the keynote, so that's what Hugging Face is, the homepage for AI. All the world's largest companies have a lot of their open source AI there. So there's a Hugging Face ecosystem as well, and I'm not going to spend too much time here because we're going to get hands-on with all of this throughout the course. We've got Hugging Face Transformers, which allows you to access, train, and fine-tune state-of-the-art models. Data sets, which allows you to store, process, and access data sets, which is the lifeblood of AI. Tokenizers, which allows you to pre-process and prepare text data, as well as vision data or any data for ML models, because one of the first steps with machine learning is turning data into numbers. And then finally, the Hugging Face Hub, which allows you to store and share models and data sets, as well as interactive demos. And so we're going to follow our Hugging Face workflow. Now, this is one of many, but it's what we're going to use as our recipe, because this is, after all, a machine learning cooking show. We start with a problem or idea. We get our data ready and we turn it into numbers and tensors. We'll see that later on. We can use Hugging Face Datasets / tokenizers for that. We pick a pre-trained model to suit our problem. We use transformers, parameter efficient fine-tuning, accelerate or TIM for this. We train our model to our custom dataset. We evaluate a model so we know that's performing well. We improve it through experimentation, trying different things. We save our fine-tuned custom model to the hub, and then we turn our model into a shareable demo that we can share a link with our friends and they can try it out as well. So what's our workflow motto going to be? As we saw on all of those profiles, what did they have in common? They had data, they had models, and they had demos or spaces. So that's what we're going to do. We're going to start with data, we're going to build a model, and we're going to build a demo. So sing it with me. Data, model, demo. Data, model, demo. Data, model, demo. You'll probably be sick of that by the time we finish this course. And so if we have a sneak peek of what we're going to build, we have 2 end-to-end projects as at the time of recording this video ready to go. That's text classification with Hugging Face transformers and object detection, which is detecting where something is in an image with Hugging Face transformers as well. And of course, both of these are end-to-end. We start with data, we build a model, we build a shareable demo. And of course, coming soon, but no spoilers, will be LLM fine-tuning, large language model fine-tuning, and VLM fine-tuning, which is vision language model fine-tuning. But if you're watching this in the future, these may already be on learnhuggingface.com by the time you watch this. So without any further ado, let's code. Now, you might be asking, what is text classification? Well, text classification is one of my favorite machine learning problems. The reason being is because it's so prevalent in so many workflows. So what we want to do with text classification is we want to categorize text into one class or another. Now, text is a very verbose term here because text can be a word, it could be a sentence, say, for example, a comment on YouTube, could be a paragraph, an email, is that email spam or not spam? Or a document, is that document business related? Or is it an insurance claim or something like that? And now, class can be any single category. So in our case, a category might be an email as a paragraph. Is that category 1 could be a spam email, category 2 could be a not spam email, category 3 could be a shopping email, something like that. So it's very broad, but I just want you to think about that text. We want to take a piece of text and we want to use a machine learning model to classify that text. So let's have a look at an example. Now, this is a problem I've actually personally worked on as a machine learning engineer for a large insurance company. They weren't called Lime Insurance Co., but that is a pretty cool name. And what they wanted was, if someone types in a claim if they had an accident, and I hope they're all right, so they type into the app, someone crashed into my car, or I accidentally crashed into someone's letterbox. So they type that into the app, and then a model processes that text, so turns the text into numbers, and then classifies it into who was at fault. That's the main question we were trying to answer with that problem. As in, if the person who submitted it, were they at fault? Was it their fault that the accident happened? Or was it not their fault, so someone else's fault? So in this case, someone crashed into my car. If our model was working well, it would be not at fault because it was someone else's fault, right? And then we have I accidentally crashed into someone's letterbox. In this person's case, they were at fault because they were the person who crashed into the letterbox, right? And now you could think about this you could write a bunch of rules of if the text contains the word someone or if the text contains the word I, then that's not at fault or at fault. But because this company was receiving thousands of insurance claims a week, there'd be so many rules, you couldn't program in them all. So we had to train a model. And our model actually got to about 98% accuracy on the test data set and would work on thousands of samples an hour. Like that was its capacity. It didn't necessarily have to do that, but it could classify thousands of samples in a few seconds. So it was a pretty good model. And we're going to build one very similar to the model I had to build for this insurance company. Now, the workflow here it wasn't just a model. It was then, this is an important thing to think about, is what happens after you build the model. Our claims could now be forwarded to the right department. So this is something to think about in your own workforce, or if you're looking for a job, is if they have a problem that involves text, and that text has to be, if ever you find someone manually sorting text into different categories, then you should start to think about, can a model be trained to do that sorting? So speaking of more text classification examples, so we have email is spam, not spam. There's my email there. If you want to send me this spam email, feel free. We'll see if my spam filter works on my inbox. So this is binary classification. So one class or another. So we're just trying to go not spam, or not at fault, at fault. Then we have what tags should this article have? This is known as multi-label classification, where one article, say this article for deep learning on Wikipedia, can have multiple label options, so tags. You could think of this as a multi-label could go on a product description on Amazon, for example, and it could have multiple different tags of what that product relates to. And then we have multi-class classification, so one output class of many. Now, this is a comment on my YouTube channel. Thanks for the video, Australian ML Chad. Really, that made me laugh a lot, right? So if we had a machine learning model that was trained to classify YouTube comments, and potentially we want to prevent toxic comments, and YouTube probably have this implemented somewhere in their system, but in this case, it was mostly funny, right? So I would classify it as funny. So in that case, the model would do very well. It was also a little bit of a good comment, so 17%, toxic 0% because it's not a toxic comment, and spam 1%. It's not very spammy at all, so it's very low there. Now, there are some more text classification problems. This is just an overview of where I want your brain to start thinking about where can I classify text. So text classification is prevalent in almost any business situation. So we might have a spam/phishing email detection. Is it email spam or not spam? Or is it a phishing email? So this is binary classification, one thing or another. Sentiment analysis. Is a piece of text positive, negative, or neutral, such as classifying product reviews? Say if you're Amazon and you want to find the best product reviews, which ones are saying that the product is good? Which one says that they're bad or neutral? Or if you're a product company and you want to find out what are the good comments about your product? What are the bad comments about your product? This would be multi-class classification. And then we have, say, topic classification. So if you're a news company, what topics should this news article belong to? That would be multi-label classification if you wanted to give it more than one tag. So this is what we're going to build. The project is food, not food. We're going to work as an intern at Nutrify. So that's my startup company, a food app, and build a food, not food binary text classification model and deploy it as a demo. So this is based on a real life model that I actually use in the Nutrify app. And so what we're going to do is use image caption text, say a photo of sushi rolls on a white plate. The label, that would be food. And we want to train our model, and then we want to turn it into a demo. So remember the motto, data, model, demo. For the data, we're going to use Hugging Face Datasets. For the model, we're going to use Hugging Face Transformers. And for the demo, we're going to use Hugging Face Hub/Spaces plus Gradio. So a fair bit going on here, but we're going to work through this all together. And so in this case, a yellow tractor driving over a grassy hill into the model, into the demo, should be not food. Well, here we've got a serving of chicken curry in a blue bowl. That's food. And hey, let's not just look at this on a slide. This is a real life demo. Let's check it out. So I'll go to my Hugging Face profile. There we go, huggingface.co, Mr. D. Burke. And this is the demo that we're going to build. Running live. I haven't recorded any video of this yet, but let's go. I love learning machine learning. Right? So this should be not food. Let's see if it works. Not food. Beautiful. Now, for breakfast, I had eggs on toast. What's this going to be? Food. Beautiful. And so one more for fun. The computer I'm using is a MacBook Pro. Submit. Not food. Beautiful. Okay, so there's our model. You can dig into the code there if you'd like, but we're going to build this. Let's jump back to the keynote. So this is what we're going to cover broadly in text form. So we'll get/create a text dataset with Hugging Face Datasets. We'll prepare our text dataset for machine learning. This is known as tokenization. It's very common with any text dataset or even image dataset or audio dataset, is turning your data into numbers ready for machine learning models. Then we're going to create and train a text classification model with Hugging Face transformers. We'll upload our trained model to the Hugging Face hub, and we'll turn our model into a demo with Gradio plus Hugging Face spaces. Whew. And the style we're going to do it is like a machine learning cooking show, right? We're going to be cooking up lots of code. Oh, sorry, one more thing. Now, you might have used an API such as GPT or Claude or Gemini or Mistral before. Now, you'll probably realize that they can classify text really well. So let me just give an example. Is this sentence about food or not food? So, my favorite place to go for a walk. The sentence is about not food, right? However, that took a fair bit of time. And so one of the main things, or the reason, and we also don't own that model, right? So one of the main things that we're going to look at is why it's important to always know how to train your own model versus using an API. The pros: you have full control over the model lifecycle, no usage limits aside from your compute constraints, can train once and deploy everywhere / wherever you want. For example, we couldn't use an API or Tesla couldn't use an API on their car. They need to use a model running on the device. Privacy-wise, data can be kept in-house / the app doesn't need to go to a third party. Speed, so we're going to see how fast our model is later on, but it is going to be quite fast. So customizing a small model for a specific use case often means it runs much faster. However, there are a few cons, but we're going to work through all of this. It can be complex to get set up, requires dedicated compute resources for training and inference, maintenance, longer development time, right? But then of course, you could always use a pre-built model API. It's pretty easy to use. You can set it up in a few lines of code. Now, there's no maintenance of compute resources. You can use the most advanced models, and it can scale if usage increases. However, the cons are that if the model API goes down, your service goes down. You have to send the data to third-party services for processing. This may have privacy issues, and the API may have usage limits, whereas your own model, you decide the usage limits. And it can be much slower than using a dedicated model due to requiring an API call. So whenever you have to do an API call, you have to send data over the internet. And although the internet's quite fast, it can take a bit of time to get there. So the dataset that we're going to use is a dataset that I've created. It's a supervised dataset. What that means is we have sample and label. And now the goal with a supervised dataset is for our model to learn the relationship between the sample and label, so that if in the future, once it's trained, we give it another sample, it will predict the most ideal label. So we have 250 image caption examples. This is a relatively small data set. However, we'll see that with the power of transfer learning, we can get pretty darn good results. And we've already seen our demo in action with just a small data set. The food, not food labels, so it's binary classification. And cool thing about this is that the samples were generated with an LLM, so they're all synthetic. That's going to be something really good to look into in the future, is synthetic data. So previously with machine learning problems, if you didn't have a data set, it was hard to build your own customized model. Now with LLMs, they're so good, you can generate your own data. So if we go to this website here, I'll just copy that, put it in here. There we go. So there's a data set there. You can check that out. I've put an example usage there. And if you want to see how it was generated, there's a Colab notebook, and I'll show you there how it was created. But I'll let you go through that on your own time. That's just an example of how we can create synthetic data and upload it to Hugging Face Datasets. We're going to go through using this data set later on though. So, where can you get help? The best thing to do would be to follow along with the code. We're going to be writing a lot of code. Refer to the source materials if you get stuck. Try it for yourself. You can press Shift Command and Space in Google Colab to read the doc string. If you still get stuck, you can search for it and then try again. You'll probably come across the documentation. Otherwise, you can always ask AI Assistant, so ChatGPT or Gemini in the notebook. Gemini is in Colab notebooks. And then we also have the Hugging Face forum, or there's a Zero to Mastery Discord chat. So we'll do our best to help you as much as we can. So don't fear, if you get stuck, we're here to help. Now, let's code. Woohoo! Welcome back. Now let's write some code, hey? To get set up, I'll show you the steps. We'll go through them, but if you want to go through them yourself, you can go to learnhuggingface.com/extra/setup. We're going to be using Google Colab, which is a free resource online. You may already be familiar with it. But to start setting it up, there's Google Colab steps there. You're going to need a Hugging Face account. So you can do that at huggingface.co/join. I'm not going to do that step because I've already got an account here. There's my account, Mr. D. Burke. You can use your own username there. And then we are going to need a Hugging Face access token. This will give us read and write access from the Hugging Face hub. So we'll see what this looks like later on of reading and writing to the hub. But for now, we're going to create our token. So if we go over to here, so huggingface.co/settings/tokens, just leave this website here. You can see all of my tokens there hidden. Never share your token publicly. I'm going to show you an example of what a token looks like, but I'm going to delete it afterwards. So leave that website there. And now we're going to go to colab.research.google.com. If you're not familiar with Google Colab, I'd highly recommend going through the example notebooks here. Do they have one on secrets? No, they don't. Well, that's all right because we're going to go through it together. So I'm going to click New Notebook. We'll just wait for this to load. Beautiful. So we don't have to call this any title, but we'll just say Setting Up Secrets Example. I don't need to save that actually. So there's a Secrets tab here. So if you have a Google account, you're signed into Google Colab, these are all API keys that you can store in Google Colab and it will remember them throughout different sessions. There you can see my Hugging Face token. It's all hidden. Now I'm going to delete mine so we can see what it's like to reset it up. I've got other things here like OpenAI, NVIDIA, Mistral, Gemini, Claude, and then if I wanted to add a new one, I can do it here. But let's go over to there. That was my previous token. I've just deleted that. Now I'm going to delete this one as well, so we can create one together. So I'm going to create one. I'm going to call it Learn HF Google Colab Token. You can call yours whatever you'd like. If you'd like to just read from the hub, you can do it like that. If you'd like to write as well, so save things, read means I want to download something from Hugging Face Hub. Write means I want to save something to the Hugging Face Hub. I like to just create one token. It's probably better practice to do one for read and write, but I like to create one that can do everything. So I'm going to tick all of these. So I just have one universal Hugging Face token. So there we go. Read access, write access, and then all of these other ones, all these other utility functions. So then I go down here. I'm going to click Create Token. Now you can see that, but by the time you watch this video, this will have been deleted. So copy your token, save it in a safe place. Do not show it to anyone. So I'm going to copy that and then come over to here and I'm going to go HF token. Type it in there. HF token is the default name as far as I'm aware. So I'm going to save mine as that. I'm going to copy it into there, the token that I just copied. Once I get out of this, I won't be able to see it again. So just keep that in mind. And then I'm going to turn that off. So HF token. So now if I turn that on, Google Colab now has access to my Hugging Face read and write token. And let's see how we can access that token. Hugging Face is going to recognize this behind the scenes for us, but if we wanted to programmatically access it, we can type in this code here, userdata.get, and then I'm going to write in HF token. I'll call this HF token equals that, HF token, and we'll see if Google Colab does indeed have access to this. I might just save it here. Let's make sure that these agree. True. Beautiful. So that's how we do it there. Now to clean up, I'm just going to show you that I'm going to delete this so that it doesn't exist anymore. Delete, that's gone. So now if you copy this token somewhere, it's going to be unusable because it's now deleted. But that's what we're going to have to do. If you want any more setup steps, you can go there. But that's the main one we have to do. We need access to a Hugging Face token throughout this project or throughout all of the Hugging Face projects that we're going to do eventually. So if you want to access it manually as well, you can import the Hugging Face hub. You will need to install it in Google Colab. So pip install Hugging Face hub. We'll let that run for a second. Oh, it might already be there. That's beautiful if it is. And then we can copy this code and it will give us an option to log in. Now you can add your token there. I can put in my token, but it won't work because I've just deleted. Yeah, there we go. So that's how you can log into it with code, or you can add your secret token there. So with that being said, let's now start. We've got the token set up. Let's now start writing some code to use the Hugging Face hub and all of the Hugging Face ecosystem. I'll see you in the next video. Welcome back. Now that we've set up our secret token here, we can start to write some code. So I'll just put in the reference here, or maybe we put in a heading. So learning Hugging Face. We're going to do text classification tutorial. Beautiful. And then say resource notebook is over here. I'll open this one. learnhuggingface.com/notebooks, Hugging Face text classification tutorial. And then I'll go set up steps. This is for Google Colab, by the way. We've gone through those. If you'd like to get up and running locally, you can do that as well. There'll be some steps in here that you can see there and try that out. We're just using Google Colab for this notebook because it's the most accessible to everyone. So the setup steps is over here. Beautiful. And I'm just going to rename this. Instead of setting up secrets example, make sure you tick your HF token access here, by the way. It will ask for it programmatically later on if we haven't ticked that, but we can just tick it manually by default. So I'm going to call this learn HF. What's our original notebook called? Well, Hugging Face text classification tutorial. I might do that. Hugging Face text classification tutorial. And I'll just append video on the end here so that you know that this notebook is the one that we wrote throughout the videos. And actually, there is one more step. A GPU is needed on Google Colab. So to set up a GPU, you can go to runtime, and then we go change runtime type. I'll show you all these steps. Change runtime type, and I'm going to select a GPU. This is going to reset my runtime. That's okay. You can choose any of the GPUs here. T4 is probably the entry level. L4 is a bit faster than T4. A100 is the most powerful GPU that Colab gives you access to, but it does require credits. I'm not sure if the A100 is available on the free tier either. I do have Google Colab Pro, but I'm trying to use the free resources as much as I can. I'll click save there, and runtime, change runtime type, hardware accelerator, GPU. Beautiful. So now you'll see that we've got a GPU there, a GPU backend. Okay, we've set up here. So if we wanted to import all the libraries, that's going to be our first step. Let me write a heading here. So import necessary libraries. So I'm going to press Command MM for that. Where is our text classification notebook? So this is, why don't we just keep the same headings as our notebook 2. So you'll see in the notebook that all the intro stuff that we went through, if you want to reread through that, that's in the notebook there. But now we've got some code to write. And I've put the note here that we do need a GPU. And so again, this is just what I'm going to be referring to. We're going to write all this live. If you wanted to just copy and paste, you can do that. But we're not in the business of copying and pasting. We want to learn this stuff. So I'm going to delete that. Let's write it together from scratch. So we're going to install dependencies. So this is mostly for Google Colab. If you are set up locally, you won't necessarily need to install them after you've installed them already. So try import datasets, evaluate, accelerate. So I believe Colab comes with transformers, import transformers. So that's Hugging Face transformers. So if we just search that, Hugging Face transformers, here we go. We get the documentation there. Beautiful. As I said, this is your extra curriculum, is to read through this for at least 10 to 15 minutes, but we're going to be focused on using it. So transformers is already there in Google Colab. However, if we try to import datasets, this is why we have to install it. We don't get datasets. So no module found datasets. We're going to fix that. And then Gradio as well. Import Gradio as GR. So if we can't do that, we're going to get this module not found error. So this is where we can do a little try and accept block. So this is saying try to import these libraries, except module. Oh my gosh, we're getting AI autocorrect here. I'm going to try and avoid using AI autocorrect as much as possible, just because I want to practice writing code. So pip install, I'm going to use U. U stands for upgrade. Datasets, evaluate, accelerate, Gradio. Okay? And then after it's installed, I'm going to re-import it. Datasets, evaluate, accelerate. Beautiful. I might turn off auto completions at some point. Settings, AI. Yeah, here we go. Editor, automatic close. Yeah, there we go. Okay, I've turned off automatic. You can keep those on if you like, but I just want to practice writing code. That's how I prefer to work. So import Gradio as GR. Wonderful. And we're going to need a few other things later on. We'll see these in use. Random, the module from Python. I love using random to sample datasets. NumPy, going to use NumPy as PD. And going to import Torch and import transformers. These all things, so Torch is PyTorch. If you're unfamiliar with PyTorch, you can go to my other website, which is learnpytorch.io. There is plenty of materials there to learn and many more Zero to Mastery videos as well. So that should look good. Now let's print out the versions. Print, I'm going to go using transformers version. So this is where I can go transformers dot double underscore version. And I can do the same thing for Torch using Torch version, Torch dot version. These will be the main ones that we need to make sure that as long as your version number is higher or equal to mine, we should be fine. So datasets version, datasets dot version. So you can, this code is to run locally or on Colab. Oh, actually, it won't print out the version. We got to install that. Yeah, so if you come back to Google Colab, if this runtime disconnects, and it's going to delete everything. So Google Colab, that's an important point, is transient. Because it's a free resource, it's not going to store all of your files here over time. So if we upload or save anything here, just be mindful that if Google Colab times out, I'm not sure the exact time, it might be an hour, it might be 25 minutes, but if you're using it, it shouldn't time out. If you stop using it, it will time out. Like if we quit this and come back 3 hours later, we can probably assume that our code will still be here, but all of this installation stuff won't be here. So just keep that in mind. If you come back to your notebook, you're going to have to reinstall this and you're going to have to rerun the cells that are above. So for example, if we ran 20 code cells here, and we come back after a break and we're up to code cell 25, we have to make sure that all of the other cells run. Here we go. Request. So this is another thing to remember, is that if you install new libraries on Google Colab, sometimes you have to restart the session to use those libraries. So let's restart our session. That'll clear everything, right? If we ever have to restart the session, which is fine. We restart the session, it connects back pretty quickly, and then we should be able to run this cell without installing anything. So it's going to import these, should successfully import because we just installed them with this command here. The exclamation mark means run this in the command line. There we go. Beautiful. We now have all of the resources we need to build Food Not Food, our first Hugging Face text classification project. So we have Transformers version 4.42.4. Now, don't worry too much if yours is way above mine. Transformers gets updated quite frequently. Torch version 2.3, your version should be at least 2.3 or higher, and same with datasets. So as long as your version on your machine is these numbers or higher, we should be good to go. So with that being said, let me just X out of this. We've now done import necessary libraries. The next thing is to get a data set. If you want to jump ahead and try it out for yourself, go for it. Otherwise, I'll see you in the next video and we'll get a data set together, hey? Welcome back. Now we've imported all the necessary libraries that we need. Let's get a data set. One of the most important steps, or probably the most important step in machine learning. So getting a data set. So because we're building food, not food, let me just write this down. Building food, not food text classification model. So need food, not food text data set. And like all good machine learning cooking shows, I have already prepared one. So if we come in here, getting a data set, I've got some information here on where you can find data sets and whatnot. This is our food, not food image caption data set. Rather than talk about it, I'd rather show you it. So we have text samples here and we have labels here. And this is a supervised problem, so we have samples and labels. The goal of a supervised machine learning problem is for the model to learn the relationship between sample and label without us explicitly writing, hey, if a sentence has TV in it, it's probably not about food. Or if a sentence has cauliflower in it, it's probably about food. So we don't want to write those rules or programs ourselves. We want our model to learn that. Now, the cool thing about this is, well, previously in the world of machine learning, it was a little bit of a challenge to find text classification datasets. And I mean, it still is. You may have one existing of your own problem, and there are resources like Hugging Face Datasets and Kaggle datasets for existing text classification datasets. But a lot of the time, these datasets won't necessarily match up with your problem. You're going to need a specific dataset. And so, in the world of large language models, or LLMs, we can generate synthetic datasets to kickstart our problem. And so a tip here is you can train on real/synthetic data. So synthetic data is data that is created by another model. But often, it's always best to evaluate on real data. But in our case, because we're working on an example problem, our data is all synthetic. So there are some blog posts there that you can check out, but I'd rather show you how I created this synthetic data set. So if we go to the Colab notebook, this is on all the links, by the way, if you need them, are in the home page. They're in the resource notebook, but there's also project, text classification. Here's our data set, our model, and our demo. We're going to create these throughout, but that's just so you know where the links are. Okay, there we go. And so this is how I created the data set. This is a little bit of extra curriculum. And so I generated them with Mistral. So if we go chat.mistral.ai, and I want to show you an example. So can you generate me a JSON of 20 image captions with the fields text, label, and the image captions should be a mixture of captions about label. This is not a perfect prompt, by the way, and label not food. For example, food caption is my favorite food is ice cream. Not food caption is a yellow tractor driving over the hill. Let's see what it comes up with. So again, it's not perfect, but these large language models are pretty darn good. Here we go. Wow. Okay. There we go. So now we've got a JSON of different food labels. So you could repeat this across many different LLMs if you wanted to. You could actually programmatically do this, but I'm just giving you examples of live on the fly. This is meta.ai. There we go. Right? So This is how we could quickly bootstrap a binary text classification dataset, and it's exactly what I've done. So if I've got pizza captions, sushi captions, curry captions, fruit captions, vegetable captions, and then I add them together. And then I've got not food captions, right? So there's about 100 or so of those, 125 maybe. And then we add them together, all items, merge them together, there's 250, turn them into a data frame, import datasets. And so here's what our data frame looks like. That looks a lot like our dataset on Hugging Face, doesn't it? Dataset, there we go. There's my Hugging Face write token. It uploads it, and then we can load it back in and get a random sample. So that is exactly how I created that. If you want to see that for yourself, you can go to this Google Colab notebook. Synthetic data generation is evolving as a practice. So that's only one quick example that I showed you in live time to create bootstrapping a data set. So this is like synthetic data is something that you can use to boost your existing real data, but you should always try to evaluate on actual real data. Keep that in mind. So we've gone through dataset creation. Now let's see how we can import this dataset. One of the perks of using Hugging Face is that we can get a code example of loading that dataset. Now you can copy this if you like, but again, I'm in the business, or we're in the business in this project of writing code. So let's do that together, hey? So we want from datasets, import load dataset. So now we can go dataset equals, we could do datasets.load dataset, but we'll just do load dataset, and then we type in here the path to our dataset. To get that, I could type it out if I know it off by heart. It's going to be my username. Just remember in the future, if you upload your own dataset, you're going to have to change my username to your username. We can click this copy button to save typing it out fully. Now, I know I said I'm in the business of writing things, but for names and stuff, we can copy it. So there we go. Path equals that. And now let's have a look at the dataset. Now, just beware that if your HF token isn't ticked on here, you may get a pop-up and it will say, do you want to allow access to your HF token? And then you can click yes, or you can just tick it on there in secrets. So beautiful, there's our data set. So how about we inspect it? We see we've got features, which is text and label, and we have number of rows, 250, so relatively small. Let's see what features we have. So what features are there? So dataset.column names. What do we have? Okay, so we have a training dataset. So that's our split. By default, if you upload a dataset to Hugging Face and you don't define splits, it will all be training dataset. So recall in machine learning that a training and test split, we'll see this later on. Training is the dataset you want your model to learn patterns on. The test dataset is the dataset you want to evaluate your model's patterns on, or learned patterns. So let's access the training split. So dataset, and we'll see what's in trained. Okay, beautiful. Now, how about we look at some random samples? So we can go dataset, access train, and we get the 0th index sample, creamy cauliflower curry with garlic naan featuring tender cauliflower in a rich sauce with cream and spices served with garlic naan bread. See, again, these are synthetic captions. They're not the best quality of data, but they're a food-based image caption, you know what I mean? So it's good enough to see if we can sort of bootstrap a model. Now, dataset, let's see what would happen if we didn't use train. Invalid key. Please first select a split. So that's something you're going to come across. And now what if we change this to test? Well, it's going to be an error as well because we don't have a test dataset just yet. All of our samples are by default in train, but that's okay. We're going to create a test dataset later on. Now, how about we inspect, so random samples. This is one of the things I love to do with any new dataset. If I've never worked with a dataset before, the first thing I'll do is I'll spend probably up to an hour sometimes just looking at random samples. That way I'm becoming one with the data. I'm trying to get a mental model of what the data looks like in my head so that when I train a model, I kind of know what's going on. We've already imported random, but I'll just show you it here anyway. Import random, and then I'm going to go random.sample. I want to sample something from the data set, and I want to get a random index that is the length of our training set, or our whole data set. So that's going to give me 5 random indexes. Let me make sure that's going to do that. Oh, typo there. There we go. So these are the random samples I'm going to check out. And of course, we don't have to, or we could just print that, hey? Random indexes. And random samples is going to be equals dataset. Now, we can index on our dataset with multiple indexes. Random indexes. So let's have a look at our random samples. There we go. Okay, now it's not formatted too well. Kohlrabi in a bowl, sprinkled with salt and served with a side of yogurt dipped for tasty, unique snack. Kohlrabi, that's a delicious vegetable. Colourful area, rug, brightening up a living room. So that's not food, and that's not food as well, but this is food. And we've got our labels down here. Let's prettify this up, all right? So print, we'll get a little info. I like to start it off with info, and so we go random samples from dataset. And then we'll go new line, and go for item in zip. We're going to zip together the random samples and text and random samples label. So these are the keys I'm getting of our dictionary. This is a dictionary here. And I'm going to zip together those, and then I can do print text, and I'll get item 0 because we have item here. Or maybe I could just do for text label, and then I can just go text, and we go labeled label. Let's see what this looks like. There we go. That's much better. So there's a wooden hanger holding clothes on a rack. That's not food. A uniquely presented sushi roll, such as a hand roll or sushi burrito. Beautiful. A whole papaya. You get the point, right? So you might go through this a few times. Our data set's relatively small, so you probably start to see duplicates. I'm familiar with the data set because I created the data set. But if you're working on any other problem, especially a data set, a text data set you'd never seen before, this is what I'd highly recommend doing. Going through 100, 200, 300 samples and just visually looking at them. That's our motto, the Data Explorer's motto: visualize, visualize, visualize. So we can get a few more different things about our data set here. So this is, by the way, because it's already a Hugging Face data set. So we'll get unique label values, dataset train.unique, and we'll have a look at our label. What labels do we have? So in our case, we only have food and not food, so it's binary text classification. But if you went to huggingface.co/datasets, we've got many, many datasets here, but we can filter it down to use text. And then, is this going to change it into, oh, there we go. Yeah, text classification. Now, just be in mind, this Hugging Face is rapidly evolving, so this might change a little bit, but if you go to huggingface.co/datasets, I don't think that URL should change too much. But if we go to text classification, there's a whole bunch of different text classification datasets here. And then we can go to another website, paperswithcode.com, datasets, and there is also text and text classification, many different datasets here that you can try out. We're just using our own sort of dataset. And then, of course, there's Kaggle datasets. So let's go back to our notebook, and we can, so if you had, maybe you might have 10 labels or you might have 5 labels, depends on the type of problem you're working with. We can check the count of each label with counter. So this is another helpful step. We're doing data exploration here. We're getting a feel of the data set. Import counter. Now, ideally, if it's binary classification, we'll have the same number of samples for each label. So dataset, train, and label. This is Python's collections.counter, by the way. Just want to show you this. Python collections counter. Yeah, collections. And then if we go to counter, you can read the documentation there. I always encourage just reading the documentation at least once with every new method that you use. Let's see what we have. Beautiful. So in our case, because our data set is synthetically generated, I've purposely made sure that we have the same number of samples. And this is something to think about going forward, is that if you have a data set that's unbalanced, potentially you could use an LLM to help balance that data set by generating new samples. But that'll be a case-by-case scenario. Now, if we wanted to turn it into a data frame and inspect our data set like that, we definitely can. Hugging Face Datasets works well with data frames. So turn our data set into a data frame and get a random sample. So food, not food, df, I'm going to call that pd.dataframe because we've already imported pandas. I'm going to send our train split of our data set there. I'm going to go food, not food, df.sample. Maybe we get a few samples, 7 random samples. Let's see. There we go. Okay, beautiful. And then, of course, now that it's in a data frame, we can get the value counts. Just many ways to do things here, you know? Label, and get the value count of the labels. Value counts. Wonderful. So food, not food. Now, our data set is in text form with a label. This is great. This is human readable, but it's not quite yet machine readable. So we have to turn it into numerical representation. So that's what we'll begin to do starting in the next video. So feel free to jump ahead if you'd like. We need to prepare data sets for text classification. Give that a shot yourself. Otherwise, we'll do it together in the next video. I'll see you there. Welcome back. Now we've got our text data set. Let's prepare our text data for classification. And this is going to be a universal process for almost any kind of text data or even image data or audio data that you work with. The main two is tokenization, or in other words, turning our text or insert other data type into a numerical representation. Remember, machines prefer numbers rather than words. And we need to create a train/test split. You may have already given this a go, but let's now do it together, hey? Here, I'm going to go 4.0, which is preparing data for text classification. Beautiful. So I'll just write down what we want to do. We want to, 1, tokenize our text, which is turn our text into numbers. This goes for labels as well. So we have words and we have labels, but we want these both to be numeric forms. And 2 is we want to create a train test split. So want to train our model on the training split and want to evaluate our model on the test split. Because right now, by default, our data set is only a training data set. So if we have a look here, we only have one split. So if we go train, beautiful. And now if we try to do test, well, we don't have that. So let's start by creating a mapping. So we're going to map our labels to numeric value. So create a mapping for labels to numeric value. And now this is going to come up later on when we actually train a model, but there's a little idiom, I guess you could call it, which is ID to label and label to ID. Now, these are just Python dictionaries. We can create them like this, which is going to be the ID of our not food label. Just a tidbit in binary classification as well. The negative class or not something is usually 0 and the positive is usually 1. Of course, we could switch these around. It doesn't entirely matter, but just for our sake, we're going to use this pattern. And this is if we're creating it by hand, right? And so the label to ID will just be the reverse of the above. So this is a good way that we can just go back and forth between our samples and convert them to a number or convert them back to their label. So let's print out the mapping, print ID to label, and print label to ID. So we've got mappings. There we go. Beautiful. Now, there is going to be a little problem, though, if your dataset had many labels. Say, for example, it's not too strange for a text classification dataset to have 5, 10, maybe 20, maybe even 100 different possible labels. So let's see how we can create the mappings programmatically. Create mappings programmatically from dataset. This is a good habit to get into, by the way. Anytime you can create something programmatically rather than hard coding it, it's generally a good option to take. So that way, if we developed a function for this, we could just pass in any dataset and it would work. So I'm going to do the ID to label is going to be index for label for IDX label in enumerate dataset train dot unique, and we're going to pass in label here. So let's see if this works, hey? ID to label. Beautiful. Now, what is actually happening there? So let's just print it out. Our dataset only has 2 examples, so it's not going to be that great. But this is a dictionary comprehension or a list comprehension. So if we were to print this out, let's go ID to label equals an empty dictionary. And then we go for IDX label in enumerate dataset train unique label. So this would work no matter how many labels that we have in our dataset. And then we're going to create a ID to label is going to be the index equals the label. And we can actually print this. So print IDX label. I spelled that wrong? Yes, I always spell unique wrong. Beautiful. There we go. And then if we have a look at our ID to label one more time, we've got the same thing. Now, to do the reverse, we can get, let's go label to ID. We can just reverse the ID to label. So we can do a reverse dictionary comprehension for label to IDX for IDX label in ID to label dot items. And then we go label to ID. Beautiful. So that's exactly what we need. I'm going to move this up here. Just put that there. And then I'll keep that one there just in case we want to have a look at it. And then I can go print ID to label, print label to ID. So we're going to need these mappings later on. And there we go. Okay, so now what can we do with these mappings? What do you think we have to do? Well, we of course have to map them to our labels. So we want these to be 0, 0, 0, 0, 0, 1, 0. And then if we sample some more, same thing again, 0, 0, 1, 0, 0, 1, 1, etc. Because that'll be good for our machine learning model. It wants to look at numbers, not food, not food. And that's the case for any labels that we have. So let's create a function, turn labels into 0 or 1, binary classification. So def map labels to number. And I'm going to pass in example here, because what we're going to do is we're going to iterate through our data set and map this function. So we'll see what that looks like. I'd rather show than talk, actually. Example label equals, we're going to map them with our label to ID, because right now, this is our label to ID, this one here. Right now it's in text, so we want to go to the ID. So we want the index, so the value here. So label to ID equals example label. We just want to update the example. And then I'm going to return the example. And it doesn't matter that we're overriding it here because we've got a reverse map as well. So if we want to go backwards, we can reverse map it. So we're converting label to ID, but if we want to go back in the future, we can do ID to label. That's why we create both of these. So let's do an example sample. Each one of our samples is going to be a Python dictionary. So this is a sentence about my favorite food, honey. I actually just had some honey. I love honey. And then label is actually food. Beautiful. So let's test our function. Test our function, and we're going to go map labels to number. And then we're going to pass in our example sample, and what should, example sample. What should we get back? There we go, label 0. Now, wonderful, that's done for one sample. How do we do this to the whole thing? Well, good news is we can map our data set labels to numbers, the whole thing. And we can do this with the map. So we can do this with dataset.map. And if we look this up, we go Hugging Face Datasets map. There we go. So do we have map? I'll let you read through the documentation here, but this is what we're doing. There's the example, very similar. And then we can call map on our data set. Beautiful. So I'm going to link this here, documentation. This is all in our sample notebook as well. Oh, excuse me. Always good to read through. This is probably a great page to read through, is go through the tutorials here. That's going to be extra curriculum. I've already got that in the notebook, right down the bottom. Extra curriculum, or exercises and extensions, but we're going to focus on writing code for now. So we're up to here, and process map. That's what we're going to do. A big step of all machine learning problems is preparing your data set. So let's see what this looks like. Dataset equals dataset train. We want to do it on the train split because that's the only split that we have. And we're going to go map labels to number. Beautiful. And then we'll have a look at our dataset. The first 5. Wonderful. That's done exactly what we need. So we've got our captions here, food and not food, and we've got 0 for creamy cauliflower with garlic naan. Has this done the right one? 0 is food. Oh, excuse me. That's because that's not the right way. We want it to be 1 as food. Let me fix this, and I'll pause the video here and I'll fix it and I'll show you what I did. Okay, I figured out what happened. Was because this is getting sorted in alphabetical order, we have to reverse our list. So we can do that with that. So that means it's going to reverse this. Let's just look what that looks like, eh? Oh, excuse me. Train unique dataset. Oh, there we go, because we've already pre-processed it later on. There we go. Reverse it. And now if we do this, we don't reverse it. There we go. Okay, so that's what we needed to do. So let's get rid of that. Let's get rid of that. We might have to reinstantiate our data set, which is no problem. So I'm just going to recreate the data set. And we'll go down to here, rerun all of these cells. And now this should work here. There we go. So 0 is not food, 1 is food. That's correct. That's how we wanted it. 0 is food. Yeah, so we have the same problem here. So we can go -1 to reverse the list. Oh, excuse me. There we go. 0 is not food, 1 is food. And then when we map this, we should have label as 1 because that's food. That's exactly what we wanted. All right, troubleshooting on the fly. So just keep that in mind if you're working with a binary problem and you want them in a certain order. If we had more classes, this may not matter. Say if we had 20 classes, the order actually may not matter too much. Just something to keep in mind if you're doing a binary classification problem and you want the negative class to be 0 and the positive class to be 1, which is generally what you'll find in example problems. So now we can shuffle the data set and have a look at 5 more random samples. So shuffle data and look at 5 more random samples. So data set, shuffle, and what do we get? Beautiful. A close-up shot of a cheesy pizza slice being pulled away from the pie. Oh my goodness. Working with food and not food makes me hungry. There we go. Label 1, bicycle, 0, wooden cutting board, 0, white porcelain sink, 0, sweet and spicy sushi roll with ingredients like mango and jalapeno, 1. Beautiful. That's all we want. So now we're going to split the data into training and test sets, but I'll save that for the next video. You might want to jump ahead and see if you can try it for yourself. Otherwise, I'll see you there. welcome back. In the last video, we turned our labels into numbers, and we're on the journey to also doing the same for our text samples. But for now, let's do another important step in all machine learning pipelines, and that is split the data set into training and test sets. So we'll write here, train set equals model will learn patterns on this data set. So it's trying to learn the relationship between the sample and the label. And the test set is model will evaluate patterns on this data set. We could do an optional third set, which is validation set. Optional, we can tune our model's hyperparameters on this set, but because our data set is quite small, if you had quite a large data set, I would recommend making 3 different splits. But for now, because our data set is relatively small at only 250 samples, we'll just create a training and test set. So just keep that in mind. Validation set is another optional step that we could take, but I'll leave that for some extra curriculum on your behalf to research. So how can we split our data set? So we can split our data set using datasets. This is Hugging Face Datasets, by the way. Dataset, the class, which is what our dataset is currently. And then we can use train, test, split. So if you're familiar with scikit-learn, the function works very similar to that. So if we look up scikit-learn, train, test, split, there we go. This is going to split data into training and test sets, but there is also Hugging Face Datasets, train, test, split. Processing a dataset. Oh, so this is a thing I run into quite often, is because there's a lot of different versions of Hugging Face documentation. If you find the old documentation, generally there's a link here to go to the latest version, which is exactly what we want. Train, test, split. There we go. Beautiful. So there's a functionality there. If you want to look into the documentation, there's it. Otherwise, let's see how it works in action. We give it a test size, which is the float. So say, for example, we had 100 samples and we have a test size of 0.1. What do you think that would be, the test size there? It'd be about 10 rows, because 0.1 times 100, 10 rows. Let's see how this works on our data set. And I'll just put a link in here. There we go. Okay, so split our data set into train, test, splits. So data set equals data set, train, test, split. Now, I'm going to use a split size, a test size of 0.2. This is quite experimental. You don't necessarily, if we had a larger data set, you could probably increase this to 0.3. If we had a different size data set, you might use 1.5 or 0.1, all different values here. But generally, if you have a small handful of samples, 80% on the training set, 20% on the test set is a pretty good ratio to begin with. I'm going to use a seed of 42. I don't necessarily have to use a seed, but because I am, that means that the split that I create from this data set will be the same split that you create. So a random seed it kind of flavors the randomness. So by default, this will split your data into test and train with a random ratio. However, because we've now passed the seed, that randomness will be flavored. So we should get the same splits. Let's have a look. There we go. Train and test. Wonderful. Now, what I also like to do is inspect some rows of this. So we have 200 examples in our training set and 50 examples in our testing set from a total of 250 samples. That's exactly what we wanted. 20% of the rows are now test. Our model will not see these during training. They'll only see the training samples, and then we can evaluate on this later on. So let's get some random indexes. Random IDX train equals random rand int 0 to len dataset. We'll get our train split there. And then we can go random sample train equals dataset. We have to specify the split that we want. And then we're going to index it on random IDX train. And let's see what our random sample train is. Exactly what we want. A slice of pizza with a spicy kick featuring jalapeno peppers. Coffee, table cluttered with magazines. Oh, label 0. I thought that was going to be a food. That's not food. That's exactly what we want. Oh, we got the same one. Silver toaster on oven set sitting on a kitchen counter. So that is related to food, but it isn't a food item. So that's something to keep in mind going forward. So it's a label, not food. And then we're going to do the same for the test. Always experimenting with the data. Rand int, lamb dataset, and let's have a look at test. And then we're going to go random sample test equals a dataset test, and we'll get random IDX test, random sample test. Wooden dresser with a mirror reflecting the room. That's not food. Do we have any food samples? A bowl of sliced tomatoes with a sprinkle of basil and a side of mozzarella cheese. Looks like someone might be getting ready to make a pizza there. So we've got our training and test sets. The next step to do is to tokenize our text data, or turn this into numbers. We've done it for the label. Now we have to turn this into numbers. So tokenization is its own topic in itself. So let's discuss that in the next video. I'll see you there. Welcome back. So we've done a bit of data preparation, but now it is time for us to turn or tokenizing our text data, or turning text into numbers. So rather than talking about it, I've got an example for you. So tokenization example, this is from going from words to numbers, tokens. So if you've ever used GPT or another large language model, it might seem like magic that you can type in words and get words back, which it definitely is magic. These models are incredible. However, people like words, machines prefer numbers. So there's a thing that's working behind the scenes when you type in a prompt to a large language model or a smaller model. I love learning about machine learning and building my own models. This is going to get turned into a series of tokens, which are here. So if you want to try this out for yourself, you can go to OpenAI's website. This is just one example of a tokenizer. There are many different tokenizers. I put that there on the note, is that the tokenization process will often be different between models. So although this sequence of text outputs this sequence of numbers with OpenAI's tokenizer, it may be different if you use another model. So this sequence of text may not equal this sequence of numbers. That it's just model dependent. But let's just give an example. So if we enter some text, hello, my name is Daniel, and I love pizza. There we go. So a token is about 0.75 words, or yeah, there's a ratio. Yeah, this translates to roughly 3/4 of a word. So it's about 4 characters of text for English text. And so this is made with the tick token library, but there is another library called tokenizers, Hugging Face, which is Hugging Face's implementation of various tokenizers. So if we go to GitHub, this is open source as well. Essentially, there's a lot of implementations in here of different kinds of tokenizers. It works really well with the Hugging Face transformers library, and it's quite fast. So does it have fast here? Yeah, there we go. Takes less than 20 seconds to tokenize a gigabyte of text on a server's CPU. So a gigabyte of text, that's a lot of text. But we're going to see this in action. I'll leave these to investigate on your own for extra curriculum. But let's see how a tokenizer works. We'll jump into here, Hugging Face Text Classification Notebook. And the premise, I'll just write down here. The premise of tokenization is to turn words into numbers. E.g., I love pizza. We'll go to something like, I'm making this up, by the way. We're going to see this maybe 30, 145, and 678. And then maybe 999 for the exclamation mark. Something like that. But let's see this with a real life example. So we can go from transformers. This is the Hugging Face transformers library. Import auto tokenizer. And so I'll just write down here. The transformers library has inbuilt support for Hugging Face tokenizers. And the class transformers.autotokenizer helps pair a model to a tokenizer. Now, there's a lot going on there, but let's just see this in action. We want to create a tokenizer with auto tokenizer. So, and we're going to go from pre-trained. We'll see this later on. So from pre-trained means that there's an existing model somewhere on Hugging Face or somewhere in our local computer. But we actually don't have one just yet on our local machine. So this is going to download something from Hugging Face. So we'll go pre-trained, model, name or path. And then we're going to put in here. It's going to be DistillBERT. And now this one always trips me up a little bit. DistillBERT base uncased. You'd be like, whoa, Daniel, where did you get that model name from? That is just from experience. And this is kind of a thing at the moment is in machine learning, because there's a lot of different models and whatnot. It actually just takes a little bit of practice to figure out which model you should use for certain things. So I personally know which model to use because I've worked through this problem and I've done similar problems to this. But we'll see where this model comes from in a second. I just want to download and show you first. So use the fast implementation. Now, this is going to be on by default. However, if you're doing this locally, note this requires Rust installed. And if we go Rust, lang, Rust is a programming language that's very fast. So I'm not well versed in Rust. I'm more versed in Python, but Rust is going to work behind the scenes for us and make this tokenization very fast. If you want to learn more about Rust, you can check it out there. So tokenizer. Now let's have a look at our tokenizer, hey? Ooh, hopefully this works. There we go. It's downloading a bunch of different things. There's a few files that have come down. Tokenizer config, config.json, vocab.txt, tokenizer.json. Are these here? Or where are they going to be stored? They'll be stored somewhere up here. That's all right. We don't necessarily have to jump into those folders. We can just see how the tokenizer works for now. So we have our DistillBERT tokenizer fast, the name or path. Now, if we look this up, this is going to come from, I'll show you. This is going to come from Hugging Face. There we go. This is a model page, DistillBERT uncased. I've liked that one there. And there's a bunch of different information to read through here, but essentially this is the tokenizer that was trained with the DistillBERT paper. DistillBERT paper, which is a distilled version of BERT. And BERT is a language model. So BERT was a very good model. It still actually is, but DistillBERT is a smaller version of it, but it's faster and cheaper and lighter to run, which is exactly what we want. We want good performance, but also runs faster. So I'll leave going through this paper as extra curriculum. That's if you want to see what's going on behind the scenes of our model later on, you can check that out. However, this is our tokenizer. We've got the model page here. And as I said before, if we go back and have a look at OpenAI's tokenizer, we'll compare this tokenizer to the one that we downloaded. So that's just to highlight that different models use different tokenizers. And we have some special tokens here: padding, unknown token, class, separation, mask. Let's just see how this works in practice. So we can test out a tokenizer. We have tokenizer and we have I love pizza. And what do we get? There we go. Input IDs. We get a dictionary back. These are our numerical representations of our tokens or of our text. And the attention mask here. Let me just write this down. So input IDs equals our text turned into numbers. And then the attention mask equals whether or not to pay attention to certain tokens. 1 equals yes, pay attention. 0 equals no, don't pay attention. So the reason why we have an attention mask with this is because a lot of the models that you'll get from Hugging Face transformers are transformer based, and the transformer architecture uses attention mechanism in there. And the attention mechanism looks at these tokens. So if we only wanted it to look at, say if we want a completion problem, we wanted to type in I love and it can complete pizza, it may only pay attention to these 3 tokens, and then we want our model to fill in these. In our case, we want our model to look at the whole sequence and then generate a label, but we haven't trained it for that just yet. We don't even have a model. So this is just our tokenizer going, here's our text in numerical value, and the attention mask is all ones. So it's like, to the model, pay attention to each of these. So that's in a nutshell. If you want to learn more about the attention mechanism, I highly encourage reading the Distilbert paper and then also searching something like, what is attention mechanism? There we go, attention mechanism from scratch. So if we now compare I love pizza, what do we get? We get, this is OpenAI versus Distilbert. So OpenAI equals that. Whereas ours is quite different there. So just something to note, and that's the beauty of the Hugging Face platform, is that the auto tokenizer class, auto tokenizer, auto classes, let's read about it. In many cases, the architecture you want to use can be guessed from the name or path of the pre-trained model that you are supplying from pre-trained. Auto classes are here to do this job for you, that you automatically retrieve the relevant model given the name path to the pre-trained weights config vocabulary. So we have auto model and we have auto tokenizer. So if we pass it in from pre-trained, that means we want to get this model. So if we go back to here, we look at all the files and versions that are there. We have a whole bunch of different files here. We have the vocab. This is going to give us a preview. There we go. Quite a large vocab file. We'll look at that programmatically. I won't let that load. Then there's a PyTorch model. There's a model there in safe tensor format, config, all this different information here. Now, there's a lot of information to take in, and you might be wondering, well, how did you know to use this model? Well, you can also go to the models directory on Hugging Face, and there's a whole bunch of different models here. It can be quite overwhelming to begin, but often I would just spend 20 minutes, 30 minutes interacting with all of these different things and looking at different types of models that you can use for different things. So if you sort by trending, you can also do most downloads, and you can also do recently created, different things like that. Whole bunch of different open source models here. So let's clear up some things. I'm just going to put in this, models, put a link in here to find all models. See there, model / tokenizer we're going to use is Distilbert based, uncased. Uncased means it doesn't worry about the case of text. So if we keep going with there, or actually, there's a lot of information in this video to take in. Let's just do a quick recap. So our tokenizer, we can load it with auto tokenizer. This is a class from Hugging Face that pairs a tokenizer with a model. We go here. Models are often paired with tokenizers. And then tokenizer equals turn text into numbers. Model equals finds patterns in those numbers. Okay, so we've got auto tokenizer, and then we have a way now to turn our text into numbers. In the next video, we'll explore our tokenizer a little bit more so that we know about it. But the main premise here is I would encourage you to type in a few different strings here and see how the input IDs differentiate. I'll see you in the next video. Welcome back. In the last video, we downloaded a tokenizer from the Hugging Face hub and we tried it out on a string. And now, how about we try it out on another string? You might have already done this. So why don't we do I love pizza? I want to show you how it can be different for just a single symbol. There we go. We get 99. Now, we don't necessarily have to ourselves understand all of the mappings here from words to numbers. That's for our machine to understand. We can also go from numbers back to words as well with our tokenizer if we had to. Now, let's keep pushing forward. We want to check out a few more different things that go with our tokenizer. So if we go back to the page, yes, we want to go to this page, files and versions. There was a vocab we started to load, but we stopped loading that. Let's check out what the vocab means. So we want to go we can access the vocab with the vocab attribute. So get the length of our tokenizer vocab, a few terms we should know about our tokenizer before we keep going on. So length of tokenizer vocab equals len tokenizer dot vocab. Oh, I'll just print out here. Info, we want to go number of items in our tokenizer vocab is length of tokenizer vocabulary. And then we want to also get the maximum sequence length the tokenizer can handle. So all of our inputs are sequences, right? Whether they're sequences of words or sequences of numbers, they're a sequence. And so really our problem is sequence classification. We want to classify a sequence of words into food or not food. So sequence classification. Let's check this out by going max tokenizer input sequence length. This is important to consider because if you're using a tokenizer and say it's not too much of an issue on our behalf, but if you're using a tokenizer with, say, documents that are thousands of words long, it might be worth taking into account how many words your tokenizer can actually work with. So our sequences are, let's say, 10 to 20 words maximum. But if you had thousands of words in your document, it may be important to pay attention to how big the max length is here. So print max tokenizer input sequence length. Let's see what we get here. Max tokenizer input sequence length. There we go. So we have, I'm going to put a little info tag here so it makes it look nice as well. We have a vocabulary of 30,500 words and a max tokenizer input sequence length of 512. And a max model length as well, actually. So that means if we put in a sequence that's over 512 tokens long into our model, it will get truncated. So if our input is 1,000 tokens long, our model will automatically just cut it off to 512. But we'll see that later on. I don't need to generate anything with AI there. Let's have a look at our vocab. So does Daniel, my name, occur in the vocab? So tokenizer dot vocab, and we'll get Daniel. Ooh, I'm number 3,817. Or actually, can we just have a look at the vocab? Let's check that out. There we go. Oh my goodness, look at all these different words that are in there. I'm going to get rid of that. Bicycles, wood, garment. And you'll notice that some of the words have these little hashes at the front. So the tokenizer doesn't necessarily turn exact words into numbers. It turns word pieces into numbers. So it could be a letter directly mapped to a number. It could be a whole word like wife or frowning mapped to a number. Or it could be a word piece like this could be cactus or some other word that ends in C-T-U-S. Y. Is there a single letter that we have? Maybe we go, let's see what A is. Or how about we try what X is? 1060. And what about A? And what about hello? And what about, is Hugging Face in there? Oh, key error. We don't get it. Damn it. Okay, how's our model going to deal with words that it doesn't know? What about pizza? Okay, beautiful. I'm going to put this back to Daniel. And then maybe we try something else. Why don't we try another name? Akash. Akash is not there. Well, how do you think our model will deal with words that it doesn't know? Well, let's try to pass it to our tokenizer. and we want to pass it in a cache. Oh, that did work. Hey, how come it worked like that? Well, that's because these are special tokens, right? Let's have a look at this. So we can do this. The tokenizer, convert IDs to tokens. This is a safety check so that no matter what we pass into our tokenizer, it will always be converted to numbers. So we can go back. So we can go convert IDs back to tokens, and let's see what we get. So we get the CLS at the start. This is a classification token there, 101, aka, so it broke a cache into word pieces. AKA gets 9875, and then this hash sh at the start of there is 4095, and then we have a separator at the end. So the separate token here. And we notice that is that similar up here? Yeah, there we go. We've got a separator at the end. Most of them are going to begin with CLS, the classification token, and the separator at the end there. So let's keep pushing forward. That's how it deals. Our tokenizer will deal with words that it doesn't know, that it's not in the vocab. Even though the vocab has 30,000 plus words, 30,500, there are still going to be many different words out there or combinations of letters that aren't directly in the vocab. So what if we just inputted something like that? Well, there we go. So it still works. Okay, so no matter what we feed it, our tokenizer will turn it into numbers. So how about we try with an emoji? That's a good idea. So since we're working with food, so try to tokenize an emoji, because emojis are kind of like text, right? So tokenizer will go convert IDs to tokens, and then we're going to go tokenizer, and I'm going to pass in an emoji. I can get that using Control Command Space on my Mac. Might be different for if you're on Windows. Oh, I don't want that there. I want that in here. And then I'm going to get the input IDs. So remember, input IDs is just this part of our dictionary returned from there. We get the unknown token. So if there is, the tokenizer is smart. They've thought of things ahead of time, you know. If there is something that the tokenizer doesn't know, it's going to either turn it into pieces of words, as we've seen with the gibberish, or it's going to break it into different pieces that it does know. But if it still doesn't know what it is, it's going to use the unknown token. That's pretty cool. So how about we get the first 5 items in the tokenizer vocab. Again, we're just exploring it here. Sorted tokenizer.vocab. And just another tidbit, another reminder, the way our tokenizer deals with words and unknown tokens may be slightly different to other tokenizers. This is why we put in the model name up here to auto tokenizer. So just keep that in mind. If you're using a different language model or a different model on Hugging Face, you may get different tokens back from here. Never cross over your tokenizers with different models, you know. So we have, oh, there we go. The first 5 is mostly punctuation marks. Punctuation, double hashtag, bang, double hashtag, and then apostrophe. It's a little bit hard to read for me with all these other symbols going on there. And how about finally, one last investigative piece going through our tokenizer is tokenizer vocab.items, and then we'll get 5 random samples, hey? What are the chances that Daniel comes up? Rick, 1800s, valet, Aztec, hash MBS. And then we got, so a bunch of different word pieces here, practices, one more time. And then we get Julian, extravagant bags, meet Sergey. Hey, that's a little story in 5 words. So we know how to turn our text into numbers now. And we've seen that our tokenizer will work with almost any combination of letters or strings that we pass it, no matter if it's not in the vocabulary or if it's just a completely unknown token. So we can throw anything at our tokenizer and it'll convert it to numbers. And then we can pass that to our machine learning model later on. We're going to see that later on, of course. So now let's make a function that's going to tokenize our samples just like we did with our labels. So I'll let you give that a try. Otherwise, we'll do it together and I'll see you in the next video. Welcome back. So we've seen how to tokenize our text, but let's now make a function because we've only tokenized one string at a time. Let's make a pre-processing function to tokenize text. So I want to go here, want to make it easy to go from sample to tokenized sample. And we can do this very similar to how we did before for our labels. We'll start by making a function, def tokenized text. I'll just scroll down a little bit and we'll get examples in there. Now, the beautiful thing about tokenizers is that they can work on batched samples. So we'll see this in a second. So I'll put a little docstring here, tokenize given example text, and return the tokenized text. And I'll return tokenizer examples text on our text column, and then I'll set padding equal to true. I'll show you what these mean in a second. Truncation equals true. So let's go. Padding is, so this is going to pad short sequences to the longest sequence length in batch. And this is going to truncate long sequences to the maximum length the model can handle. So for example, if our, e.g., if sample length equals 1000, model length equals 512, sample will be shortened to 512. And this is padding. So e.g., if sample length equals 100, sample will be padded to 512 or longest sample in batch. So why do we do that? That's so we can get all of our samples the same length. In machine learning, it works out computationally better if everything is the same length because it can be parallelized. But if you want to see, actually, there's a good piece of documentation on that. Let's go to here. I'll just show you what our tokenizer looks like. So our tokenizer is an instance of Distilbert fast tokenizer, or tokenizer fast, sorry. And that comes from being an auto tokenizer. And then there are several different configs in here. So Distilbert config, that's a model. But if we want the tokenizer, yeah, there we go. Distilbert tokenizer fast, that's what we want. And then if we look in here, this tokenizer is inherits from pre-trained tokenizer fast. A little bit of a rabbit hole, but that's okay. This takes a little bit of practice to go around, which is why I encourage you to spend some time in the documentation. And then if we have pre-trained tokenizer fast, if we look for padding, we want to go here. Oh, it's in the call. So when we call our function, padding, we've got some options here. Activates and controls padding, accepts the following values. So we put in here true or longest, pad the longest sequence in the batch, or no padding if only a single sequence is provided. And then there's also truncation. So truncate to a maximum length specified with the argument max length. So that's if we set it to true, which we've done. This will truncate token by token, removing a token from the longest sequence in the pair if a pair of sequences or a batch of pairs is provided. So if you'd like to read more on padding and truncation, you can go Hugging Face Transformers, and we look at the documentation there. Or you could search padding and truncation. Is it in here? Yeah, there we go. Conceptual guides. I'd advocate for reading through all of these here, just in your own time. But if you want to read more on padding and truncation and why we go through that, you can see it here. I'm going to put that in as an extra resource, padding and truncation in the docs. Wonderful. So let's now test out our function. We'll go example, sample 2, and then it goes text, and then we go I love pizza. The label in this case is food. So we'll do it as 1, and then we're going to test the function. Does this return tokenized text? It should, because we're pretty good function writers, you know. Example sample 2. Let's see what comes out from here. Beautiful. We've got some input IDs. Now, let's see if this works in conjunction. Now, this is only on one sample, so the padding is not going to come into play. How about we make long text equals I love pizza times 1,000. Okay? Let's see how long this text is. Long text. So very long, 12,000. And we might blow up Google Colab here, but we'll print it out. There we go. I love pizza, I love pizza, I love pizza. Right? Or maybe we'll put a space at the end. 13,000 now. There we go. So let's now see what happens when we pass this to our tokenize text function. So tokenize text, and we're going to pass it in. Text will be long text, and it is about food, so we'll go label is 1. What happens here? There we go. So output equals output long, or we'll just do tokenized long text equals that, and then we'll go length of tokenized long text, and we'll get the input IDs to show you that it's truncated. So see here, our input IDs, this is not 13,000 characters long. It is going to be how long? 512. There we go. Beautiful. So that's truncation. Padding will only happen per batch, so it's not going to pad this to be of a certain length because this is the longest sample in the single batch here. But truncation will work on a single sample. And that 512, again, comes from, if we go back up here, that's our max tokenizer input sequence length. So 512. And if we wanted to find out something even more, is if we go into config.json in our model file, and we find, position embeddings 512. So that's the max length of our model there. And we can find also tokenizer config. There we go, model max length. Beautiful. So let's keep going. We've got a function now. How do we put that onto our data set? So let's remind ourselves what our data set looks like. How do you think this is going to work? We've done this before with the label. So we can use the map function. Now, there's a little bit of a new functionality here I'd like to show you as well with map, but let's write this down. So map our tokenize text function to the data set. So tokenized text or tokenized dataset equals dataset.map, and we're going to go function. The function we're going to map is, of course, our tokenized text dataset function. We're going to use batched equals true. This is a powerful pre-processing step, and then we're going to set the batch size to 1,000. Now, again, this is something we could experiment with depending on the hardware we have available. 1,000 is the default, but what does batched mean? So set batched equals true to tokenize across batches of samples at a time rather than one at a time. This is a general pattern in machine learning. I'm going to write this down. Note, in machine learning, it is often faster to do things in batches rather than one at a time due to leveraging computer hardware parallelization. I always have trouble with that word. I'm not sure if I spelled it right. Parallelization in computing. Am I getting that correct? Yeah, there we go. Refers to the process of breaking down larger problems into smaller, independent, often similar parts. So parallel computing, we're using more so just processing. So what that's going to do is it's going to tokenize 1,000. Our data set's quite small, but if your data set was really large, tokenizing it may take a little bit of time. So we do it at 1,000 samples at a time. And of course, you can alter this number here. But where I got these from, these parameters, we can go into dataset map Hugging Face. We'll look up the documentation. very good practice to get used to the documentation. We'll come down to map, and we go to map over here. I'm going to bring this over to there, and a little bit of extracurricular is to read through here. So if we go to batched is false by default. So provide a batch of examples to function, and then the batch size here, number of examples per batch. So it's going to do 1,000 at a time, or try to at least, rather than just tokenize one in a for loop, if that makes sense. So I'm going to copy this in here and see more in the map documentation. Okay, now let's see this in action, hey? I'm going to have a look at the tokenized data set. Is this going to change? There we go. See how quick that was? Oh my goodness. So it didn't even take much time at all. The timer literally didn't go up a second because we have 6,000 examples per second and 2,500 examples per second on the test data set. So that is quite fast. And again, it probably would have gone faster if we had more samples. I mean, this examples per second, if you know what I mean. That would have gone up if we had a larger data set. So let's have a look now at 2 samples from the tokenized data sets, because now we've mapped it to both the train and test. We've turned our labels into numbers, and we've turned our text into numbers as well. And we still have the original text, of course, but we have now input IDs and attention mask. Remember, the attention mask is 1 if we want to pay attention to that input ID, and 0 if we don't. So let's go train tokenized sample equals, we'll just get the first one of each, hey? Tokenized dataset train 0, and then we have test tokenized sample equals tokenized dataset test, and then we'll go like that. And now we'll just have a look at the first one, train tokenized sample. See what that looks like. Oh my goodness. Yeah, so a lot of stuff there. Why don't we print this out, making it look good? Attention mask, there we go. We want it to pay attention to everything except a 0, yeah. So 0 is going to 0 out. So that's padding. Padding token is 0. We can check this by tokenizer. If we go tab, we should have special tokens. Yeah, there we go, all special tokens. And then if we want to get tokenizer all special IDs, there we go. So unknown token is 100. Separator token that comes at the end is 102. Padding token is 0. So that means we're going to pump it with zeros. So multiply anything by 0 and then you get 0. So it means don't pay attention to that. Class token is going to be 101. And that comes at the start. And see how 102 is at the end. Separator. That means the end of the sequence. And then mask. We don't have any 103s as far as I'm aware. Okay, wonderful. So let's loop through this. So for key in train tokenized sample.keys, we'll print this out nicely, hey? We'll go print info, and we'll go key, and then we'll print, go train sample, train tokenized sample key, and we'll go print test sample, and we can go test tokenized sample key here. They have the same keys, so we can just use the keys from the training sample to index on the test sample. Let's see what that looks like. Hoo-hoo, isn't that cool? Okay, so we have our text, set of headphones placed on a desk. Wonderful. I've got some headphones placed on my desk here. Test sample, a slice of pepperoni pizza with a layer of melted cheese. And then we have a label, train sample 0. So this is going to be not food. And this is going to be what? Food. And then we have our input IDs, which is our tokenized text. And then we have our attention mask. Notice how all the zeros here line up. So where the padding tokens are, which is 0, is where all of our attention mask gets set to 0. So our attention mask, we're only paying attention to these tokens here. They're the important ones. That's what we're telling our model. These are important. Ignore these. These are padding tokens. So what should we do next? Well, how about we just summarize? Tokenization is a bit of a, if it's your first time looking at it, let's break down our tokenization takeaways, hey? takeaways. We want one is tokenizers equals turn data into numbers, e.g. text, map to, we'll do that, map to number. And then 2, so many models out there and have different tokenizers. Hugging Faces. This is why Hugging Face is so helpful. Hugging Faces auto classes, e.g. auto tokenizer. There's also auto processor and auto model, etc. help to match tokenizers to models. And then 3 is that tokenization can happen in parallel using map and batched functions. Beautiful. So we've gone through a whole bunch of information here for tokenization, but we've covered, the good news is this information that we've covered will translate to many different problems that you're going to deal with on the Hugging Face platform. And we've got some more information here. All the models are available there. We've decided that we're going to use Distilbert based on K. So how would we decide that? Again, we go to Hugging Face models and we can sort through the different models on text classification. We find our problem, computer vision models, natural language processing, audio, text classification. We might want to find the best, so trending or most downloads, and we find, that ours is right up the top there, but this has been fine-tuned for a special task. We'll create our own fine-tuned model later on. So if we want to create a tokenizer / model, we can look at the auto classes. This is in the transformers documentation if you want to read through that. We create an auto model using auto model type class from pretrained. We pass it in the model name there, and then the model will often be paired with a tokenizer or a preprocessor under the same name, and we can create that with auto tokenizer. So with that being said, let's keep moving forward. Now, we're not quite up to creating a model just yet. We're going to implement a way to evaluate our model. So let's setting up an evaluation metric. So I'll leave that for the next video. So tokenization is done. Our data is officially in numbers. Let's in the next video set up an evaluation metric. So when we train a model, we know we've got a metric to tell how well it's doing on our data set. I'll see you there. Welcome back. Now, we've prepared our data. We've turned it into numbers. We've tokenized our text and we've turned our labels into numeric IDs. So the next step is to set up an evaluation metric. So what we want to do is use the evaluation metric to get a numerical idea of how our model is performing. And so some common evaluation metrics. So we're working with classification, right? For classification, accuracy, we've got precision, we've got recall, and we've got F1 score. So accuracy is what we're going to use. So how many examples out of 100 did you get correct? So for example, if our model gets 99 out of 100 examples correct, it will have 99% accuracy. And so an evaluation metric is important because some projects may have an evaluation threshold you need to fulfill. E.g., when I worked on insurance claim classification, equals required 98% plus test accuracy to be commercially viable. So they needed quite a high accuracy for the model to be deployed. And we were able to achieve that. It's not always the case, but this is why we set and evaluate our models. So that if we put them in production if we evaluate them on the test data, if we evaluate them on custom data, which we will do later on, we can know with a bit of certainty how well they'll do in production. Of course, machine learning is very experimental. These things evolve over time. And if we go back to our workflow, we see we're not following it linearly. And that means step by step. We're kind of jumping around a bit. We've already done this step, getting our data ready. We've picked our pre-trained model. We haven't instantiated a model yet, but we're using Distillbird. We haven't trained it yet either, but we're going to set up an evaluation metric so that when we do train it, we can evaluate it straight away. We can actually evaluate it during training. And so for evaluation, Hugging Face also have a library called Hugging Face Evaluate. So let's have a look at that quickly. We'll go Hugging Face Evaluate. Now, this is an open source library with a lot of helpful evaluation metrics built in. So choosing the right metric, I'll leave you to read through that for some information there. But we see here, we've got accuracy, precision. We're going to be using accuracy. So, looks like that's broken. That's okay. We can instantiate it anyway. And then if we go sklearn evaluation metrics, this is another good place to find evaluation metrics for certain problems. Classification metrics, we go here. So precision recall curve, ROC curve, and a lot of them you'll notice the trend is comparing the true to the predictions. So Y true to Y prediction. We want to compare our true labels from our data set to the model's predictions. ROC curve, F1 score, all that sort of stuff. I'll link this in here. So we'll go back to our notebook. Some places for evaluation metrics. Scikit-learn documentation. And then we have Hugging Face Evaluate. Hugging Face Evaluate. There we go. Copy that in there. Beautiful. So we've already installed Evaluate here. So to set it up, we can import Evaluate, and then we're going to import NumPy as NP. And then we're going to, from typing, import tuple. So we can do a type hint for our function that we're going to create. We're going to set up our accuracy metric, and we can do this by going evaluate.load accuracy, and we can go def compute accuracy predictions and labels. This is what our model is going to output. It's going to output predictions and labels. So we want our evaluate function to take them apart, predictions and labels, and compare the predictions to the labels. But we'll see this in practice in a second. So np.array, and this is going to be an np array. That's what it's expecting. And then here we're going to go, we'll put a doc string in there and go computes the accuracy of a model by comparing the predictions and labels. And then we're going to go here, predictions, labels equals predictions and labels. We'll separate that tuple into its own two entities, predictions and labels. And we're going to return accuracy metric compute. So this is accuracy metric has a method called compute. Accuracy metric here. And then it's going to be predictions equals predictions. And then the references, see the doc string here. We want to compute the evaluation module. So predictions is going to be the model's predictions, and our references are going to be the models or our data's labels. So we're comparing Y true here, the labels, to Y prediction references. There we go. Beautiful. Now, function created. How about we do an example? So example, predictions and accuracy score. So we want example preds all correct. And we'll create an array here of 0, 0. How many should we do? 1, 2, 3, 4, 5, 6, 7. How about we do 10? 8, 9, 10. So that was all not food, right? We can copy this, and then we'll go example threads 1 incorrect. And we'll get rid of that, and we'll change one number here to be 1. And then we want to go example labels equals np.array, and then we'll go all 10. So we'll make sure we got 10. Right, all not food, sorry, but this example with one incorrect has one food prediction. So we can print the accuracy now. So test the function. So print, what should it be? Accuracy when all predictions are correct. We will go compute accuracy, and then we'll go example. So this will be our predictions and labels. We'll pass it in as a tuple. So example predictions all correct, and example labels. So we'll put those together in a tuple, and then we'll go down here, we'll copy this when accuracy when one prediction is incorrect. So you might be able to do the math in your head. What should we get for each? Beautiful. That's exactly what we wanted, right? So accuracy when all the predictions are correct is 1.0, 100%. Accuracy when one prediction is incorrect out of 10 is 0.9, 90%. So we've got an accuracy metric. What is next for us to do? Well, we've ticked a fair few of these boxes. We've got an idea or a problem. We've got our data ready. We've picked a model or a tokenizer. We haven't yet trained and fine-tuned our custom model on the dataset. So how about in the next video, we get started on preparing for training. This is so exciting. I'll leave this here. So setting up a model for training. Again, you might want to jump ahead and check out the example notebook, see how far you can get on your own. But otherwise, we're going to build a model together in the next video and start training it on our own custom data set. That's so cool. I'll see you soon. Hello and welcome back. We're now up to setting up a model for training. This is one of my favorite parts, and we are making terrific progress through our workflow here. So pick a pre-trained model to suit your problem, train and fine-tune the model on your custom data. So let's have a look. I'll just write down the technique that we're going to be using. So right here, we're going to be using transfer learning. And transfer learning is a powerful technique unique to deep learning models that enables us to use the patterns one model has learned on another problem for our own problem. So this is one of my favorite techniques in the field of machine learning and deep learning. So we just look up transfer learning. Let's see what images we have here. How transfer learning works. This is like a pretty good image. Oh, I don't want that. We've got something better. Here we go. This is great. Yeah. So we start with a data set and a model learns patterns such as ImageNet. Now, if we look up ImageNet, this is for computer vision. ImageNet is a really large data set with 14 million images across 21,000 different categories. So you could imagine that if a model learned patterns on 14 million images and then we applied it to our own data set of images, it would do pretty well. And that is the case of transfer learning. However, in our case, if we go to the Distilbert model, we're working with text, right? So let's have a look. Where was this model trained? There we go. Data sets used to train Distilbert, the model that we're using, Distilbert base and case. We've got the book corpus and we've got Wikipedia. So what this means is that our model has essentially read all of the books in this. Here we go. There we go. I got filtered. And so 7,100 different books. So our model has a great representation. And of course, Wikipedia, which is cleaned articles of all languages. How many articles was there? Does it say here? Yeah, there we go. So many gigabytes of text and thousands of books. There we go, number of examples. So for English, for example, it's got other languages here, German, French, Italian. So we have a lot of different samples. So what our model has done is it's going to learn the patterns in, do we have transfer learning Wikipedia? Learn the patterns in text. So transfer learning Wikipedia. There we go. Is a unique technique, is a technique in machine learning in which knowledge learned from a task is reused in order to boost the performance on a related task. So our Distilbert model has got a baseline representation of language. So this model is, so the order that words should go in. And what we want to customize it to do is learn the representation between these order of words and the label. And this will go for any modality or any kind of problem, right? The same transfer learning is a paradigm in machine learning that can transfer between domains, from computer vision to natural language processing, which is what we're working with. So, transfer learning. So there's a step in machine learning models known as pre-training, where you start with a large data set and you create a base model. In our case, our Distilbert model on Hugging Face is the base model. Then you can use feature extraction, which is where you take a smaller data set and the base model, and you put a layer on top for your custom output, in our case, food or not food. And then there's full fine-tuning, which is we take our custom data set, which is often a lot smaller than the original data set, and then we pass it through the base model, in our case, Distilbert, uncased, and then we put our custom output on the top, and we train the entire thing. This is known as full fine-tuning. Now, you'll notice that there's a flame here, so this means that this layer is trainable. The icicle here, or the snowflake, means that this is frozen. That's feature extraction. So the one that requires the most compute is this original pre-training step. It's got the largest data set. It's got the base model. It's going to take the longest amount of time to go through all of those books, all of those Wikipedia pages and whatnot, and learn a baseline representation of language. So this is where the whole model is trainable. So this step has already been done for us. Now, we could do feature extraction where we freeze the base model. We'll see what that means later on. But we're going to do full fine-tuning because Hugging Face Transformers makes it very, very, very easy for us to do so. So let's, instead of just talking about it, I just want to show you a couple more example use cases that we talked about before. So in the case of computer vision, you might take ImageNet, which is 14 million images on 21,000 different classes, train a computer vision model, and then customize it to, for example, a smaller model that can identify food, such as in the Nutrify app. You take a photo of food and identifies it as what food it is. In our case, natural language processing, we use transfer learning. The model learns patterns/weights from a similar problem space of a large data set, far larger than our own data set. We train that model to learn a baseline representation. In this case, it learns a baseline representation of vision. In this case, it learns a baseline representation of language. And then we customize the models here, the underlying representation, to suit our own problem. And in this case, we often have a much smaller data set than what's available, say, the entire internet. And modern large language models often use literally the entire internet to train on, and then they get outputted into a chat domain. But in our case, we're happy to stick with smaller models and customize them for a very specific use case. Now, why use transfer learning? Well, we can leverage an existing neural network architecture, such as the Distilbert architecture, which has proven to work on problems similar to our own, right? The Distilbert architecture gets great results on many natural language processing tasks. And we can leverage a working neural network architecture, which has already learned patterns on a similar data to our own, and we often get great results on our own problems with less data. So we're going to see how good of results we can get with only 250 samples, thanks to the power of transfer learning. Now, with that being said, we've gone over the conceptual overview of transfer learning. In the next video, let's set up our Distilbert model here, and we'll start working towards training and fine-tuning that model on our own data set. I'll see you there. Welcome back. In the last video, we discussed the powerful technique that is transfer learning. Now, let's see it in action, hey? Let's write out a workflow for training. So we've got a little bit of an outline to follow. So create and pre-process data. We've actually done that. So I'll just press Command, Control, Space. We'll tick that one. And then we're going to define the model we'd like to use for our problem. And now a place you can find models is, of course, huggingface.co/models. I'll just copy that link in here. And then if we go to our target problem, we have text classification. If we open up this, of course, we can search, look through different stuff like that. But we can also go, if we go to the Hugging Face Transformers documentation, we've got options over here for natural language processing, text classification, right? This is going to be great examples. And in fact, depending on what your problem is, I'd highly recommend you checking out the different tutorials that are here. So if we go text classification, remember task guides, transformers. Is there a way to just link to? Anyway, doesn't matter. We'll go back here or see the task guides in HF Transformers docs. Number 3 is we're going to define our training arguments for training our model. And we can do so with the Transformers training arguments class. We're going to see this hands-on later on, and I'll show you the documentation for that. But for now, we're just focusing on getting our workflow ready. So once we've defined our training arguments, we're going to pass this to an instance of transformers.trainer. So these two work really well together. Transformers, training arguments, these are going to be like the settings / hyperparameters for our model. And this is going to be the trainer. So this is going to take in the settings, and then we're going to give those settings to the trainer, and that's going to train our model. And then we'll go, number 5 is train the model by calling our instance of trainer.train. And then 6, we'll go save the model to our local machine. So we can save it to our Google Colab instance or locally. So it'll appear over here if we save it to Google Colab or in your local machine. And then, of course, we could push it to the Hugging Face hub so we can share it with others and reuse it later on. And then number 7, we can evaluate trained model by making and inspecting predictions on the test data and our own custom data, of course, because the real test data set is the real world. So finally, we're going to turn the model into a shareable demo, just like we've seen before. So remember, we're interns at Nutrify HQ, and we want to build a food, not food text classifier model. So we could use this to filter a large data set. So let's train our first text classification model. This is what we're going to end up building, right? Not food. Beautiful. Okay. A lot of steps there, but nothing that we can't handle. So we've already decided that we're going to use the Distilbert base uncased model. And again, the way to find a model is by going through the models page or by going through the task guides on Hugging Face Transformers and figuring out or seeing examples of different models, because that just takes a little bit of practice, because there are a lot of models available and sometimes you just need to dig into what you're trying to work on and see which model might be suitable for your own problem. And so we come back here. Let's now set up a model. So we're going to go from Transformers, import, because remember how I discussed Transformers have auto classes? There is actually auto classes for specific problems as well. So we're going to set up an auto model for sequence classification. And then we can go model equals auto model for sequence classification, because we're trying to classify sequences. And we'll pass in the details here. So the pre-trained model name or path is going to be equal to this path on Hugging Face for now. We'll start it off with this path. Once we create our own custom model, we can enter that in here if we wanted to. But because we haven't, this model is a base model. So if we remember our transfer learning diagram, we have pre-training, then we create a base model. This is what we're instantiating here. We're instantiating the base model. So we'll just let that run. And then we need to set how many labels that we want. So num labels, how many labels do we have? We have 2 because we want to classify it into 2. So classify into food/not food. And of course, you would customize this depending on your own data set, how many labels you have. And then here's where our mappings for ID to label come in. So if you remember a few videos ago, we created these mappings. This is to tell our model what we want it to input/output. Right? So if we remember what our ID to label is, ID to label. And if we remember what our label to ID is, right? Just dictionaries that go from ID to label and label to ID. Beautiful. So you're ready to instantiate our first model? Let's do it. Hopefully it works. Oh no, what's happened here? OS error is designed to be instantiated using from pretrained. Oh, I didn't call the from pretrained. Excuse me. From pretrained. So this is from pretrained, this method here. If we look up this, auto model for sequence classification, it's part of the auto classes. So we've got from pretrained there. Now, do we have documentation here? From pretrained, there we go. So that's what we're passing in. We can pass in a config. A lot of these are set on good settings by default. But then if we come down here, we've got our Distilbert model there. But we've also got over here our auto model for sequence classification. There we go. Auto model for sequence classification. This is a generic model class that will be instantiated as one of the model classes of the library with a sequence classification head. Beautiful. When created with the from pretrained class method. So that classification head is this custom output. So that's what it means by this, with a sequence classification head. We're customizing our output to, if we go back to Google Colab, with this. This is what we're customizing the output head with. So let's load that. From pre-trained, it's going to download the model there. Beautiful. Now we get this little output here. This is exactly what we were just talking about. So some weights, so weights is another word for patterns, or that's what I call them, patterns, but they're actually numeric weights. Because our model is essentially a big collection of numbers that have learned patterns in large data sets. So some weights of the Distilbert for sequence classification were not initialized from the model checkpoint and are newly initialized. So classifier, so this is going to be the head of our model. This is the classifier output. So that's what we want to do. We want to classify text. These are the ones that we have to customize. So if we have a look at what it says here, you should probably train this model on a downstream task to be able to use it for predictions and inference. Exactly, right? So again, that head, we need to customize this. So right now we've got this part and we've got this part, but we haven't yet trained our model to do this thing. Let's see, speaking of our model, let's inspect it, hey? Model, what do we get? Wonderful. Now, there's a fair bit going on here, but this is, as we can see, a collection of transformer layers. So we've got multi-head self-attention block. These are all neural network layers that have already been pre-trained, the embeddings, the transformer model. What hasn't been trained is the classifier. That's what we're going to train on our own problem. So embeddings, let's just write this down, hey? Our model is comprised of the following parts. We have one, embeddings. So embeddings, a form of learned representation of tokens. So if tokens are a direct mapping from token to number, embeddings are a learned vector representation. So this means that if our tokens are a sequence of just integers, as we have seen up here, right? Embeddings take tokens one step further and go, I'm going to take this token and I'm going to map it to another numerical sequence that has been adjusted based on all of the other words that I've seen, right? So if we keep going, so token, direct mapping representation, embedding is a learned representation. And then we got transformer, which is our model architecture backbone. This has discovered patterns / relationships in the embeddings. So again, we're forming an even deeper relationship in the embeddings. And then number 3 is the classifier. So we need to customize this layer to suit our problem. So we've kind of gone over that quite quickly, but this is because we're not really going in depth onto what the actual model architecture is. If you'd like to know what the behind the scenes of that are, I've left a bunch of different resources here in the example notebook of how you can learn more about the transformer block there, embeddings block there. So if you want some resources on the transformer, you can read through here. The transformer architecture comes from the Attention is All You Need paper. But we're more focused on this project on using the model rather than going through it in depth. I'll save that for another resource later on. So what can we do next? Well, in the next video, how about we count the parameters of our model? So I like to think of a parameter as one opportunity to learn a pattern in the data. So we've gone through our model. We've got it so far. It's not quite yet ready to be used. So for example, if we passed in a sample of tokens, maybe we go model 1, 2, 3, 4, 5, 6, 7, 8, 9. What comes out? There we go. Okay, so we get errors. What this is basically saying is we need to customize our model so that it can work with inputs. And we're going to work towards doing that over the next few videos. I'll see you there. Welcome back. In the last video, we downloaded our first model and we saw that it's a pre-trained model. So Transformers is suggesting us here that we train this on our downstream task, which we're going to do. Our model is composed of 3 main parts: an embedding layer, which takes tokens and transforms them into a learned representation. This learned representation is from going through millions of words of text. Then we've got the transformer backbone, which is going to find even more patterns in those embeddings. And then we have our classifier layer, which is going to classify the outputs of the transformer into food or not food, because we have out features here. So I didn't quite cover the out features there, sorry, in the last video, but just know that if we change this to something else, if we change that to 5, it'll change our out features to 5. So we're outputting 2 because we have 2 labels. So if we keep going, we tried to pass our model a sample here. This could be a sample of tokens. However, we've got a type error. List indices must be integers or slices. So we strongly recommend passing an intention mask. And now this is where we have to be sure that we pass, this was the incorrect format to pass to our model. This is where we have to be sure that we pass, however our model was trained, which is with the tokenized data, we have to pass in the same format of data as our input. So although this could be 3 different tokens, it's not quite the exact format our model is expecting. Our model is expecting something like this. So if we look at our tokenized data set from before, and we go train, and then we go 0, let's see what we get from there. Okay, so this is what our model is expecting. It's expecting something with input IDs and an attention mask. This is why we're getting this error here. So just keep that in mind. I'm going to write this down. Note, if you get input errors from passing a sample to a model, make sure the sample you pass to your model is formatted in the same way your model was trained on. For example, if your model used a specific tokenizer, make sure to tokenize your text before passing it to the model. So that's what we didn't do. How about we try to pass this sample to our model? So model, if we call that, what happens there? Great, another error. Now, why do we get that? Well, it's because we have to pass all of the keys that are in our dictionary there. So we can use this special format, double star, which means basically unpack all of the keys in our dictionary here. So double star, what does this come out as? Invalid syntax. Well, okay. That just means, let's see if it works if we pass it in here. Oh, damn it. So our model we're still getting errors. You know why? Because we haven't trained it. So this little syntax here means I want to pass all of the keys that are in this dictionary to our model as input parameters. So let me just give you another example. So model, and if we go this is the same as going input IDs equals, let's see if it works like this actually. Input IDs, right? And then we also need the attention mask. Attention mask equals that, attention mask. So that's that little double star syntax in Python. And then let's see what happens here. Oh, actually, okay. So our model hasn't been trained. So we keep getting errors. Let's train a model and then we'll try it. Input IDs. There we go. Okay. For now, how about we count the parameters in our model and then we'll train it to customize. So I want to show you one more thing before we start training our model. Count the parameters in our model. So weights / parameters equals small numeric opportunities for a model to learn patterns in data. So when you hear someone is updating the weights or training the parameters of a model, just think of that as small numeric opportunities for a model to learn patterns in data. Now that's what we want to do. We want to tune the weights / parameters in our model that have already been pre-learned on a certain data set, bunch of text, to our own problem. So how do we count parameters in our model? So count params, model. So count the parameters of a PyTorch model. So behind the scenes, our model is written in PyTorch. I know that because I've had experience with Hugging Face models, and most of them by default are written in PyTorch. Again, if you'd like a primer on PyTorch, you can go to learnpytorch.io. There's a bunch of different stuff there. You can also look at PyTorch Transfer Learning, which is a more in-depth version of what we're working through here, but I'll save that as extra curriculum. So we're going to look at our trainable parameters. And the way we get that is we sum the param number of elements, so numL, that's what that is for param in model.parameters if param requires grad. So requires grad means requires gradient. This means that a parameter is going to be updated with gradient descent during training. Now, if we look up PyTorch requires grad, you can read about, there we go, what requires grad is. So if requires grad is true on a certain parameter, it's going to be updated during training. If it's false, it won't be updated during training. So that's a trainable parameters, and we can figure out the total parameters is going to be the sum of the param numL for p or param, in model.parameters. We can have a look at these by going model.parameters. These are going to be all the numbers that our model is going to use to find patterns in our data. Oh, can we get list? Is that going to come out? Okay, there we go. So there's a lot there. So these are all the numbers in all the layers of our model. Look at that. How cool is that? All of these numbers, somehow, I can't even decipher what's going on, and I've trained many models, but somehow we pass in, this is the magic of deep learning, we pass in, I'm still scrolling, this is incredible, we pass in a tokenized sample, and it goes through all of these numbers. It gets operations, it gets multiplied, it gets added, it gets subtracted, all that sort of jazz, and somehow it's going to learn a representation of the data we pass it in. Right, so all of these, each one of these is a small opportunity to learn patterns in the data. These are what you hear when someone says adjust the weights. these are the weights of our model. So I'll let you read through those, see if you can decipher what's going on there. But what we're going to do is just, with our little function here, is count all of those parameters. So let's now return a dictionary of trainable parameters. And then we go here, trainable parameters, and we'll go total parameters. So for our training workflow, all of the parameters should be trainable because we're doing full fine-tuning. Total parameters. And then we'll go count params on our model. Oh, count parmas. Like I'm counting chicken parmesanas, you know? There we go. Okay, beautiful. So looks like our model has 66 million or say about 67 million. So it looks like our model has around 67 mil parameters, and all of them are trainable. Now, a little tidbit here is note, generally, the more parameters a model has, the more capacity it has to learn. Now, for comparison, models such as Llama 8B or Llama 3, which is a large language model, has 8 billion parameters, right? So something over 100x our model. So if we do 67 million or 8 billion, 8, 1, 2, 3, 1, 2, 3, 1, 2, 3, divided by our model, 67 million, has over 100, about 120x the amount of parameters. So if we look into our model, just something to take into consideration for problems that you're working on. We have files and versions. This is our model. It is 268 megabytes. So remember, if we want to use this in an application, we need to have 268 megabytes of space, and we need to be able to run that file. Whereas if we go to models and look at some of these large language models, which perform very well, Facebook's 405 billion parameters there. Let's have a look at this. Do I have access to this yet? Files and versions. Yeah, there we go. So this model is going to be, this is 8 billion parameters. 1, 2, 3, so 15 gigabytes, 16 gigabytes, right? Versus our model, our small but nimble model, 268 megabytes. And so it can get, these models can get very big. So I'm going to write a little note down here. If you want the best possible performance, generally more parameters is better. Now, a note, however, with more parameters requires more compute plus time. And you'll be surprised, as we're going to see later on, spoiler alert, how well a smaller model can perform with specific data. So just keep that in mind. Now, I'll let you explore some more models on here and just check out, so this is another large language model, DataComp large language model from Apple, 7B, so 7 billion parameters, which is 1, 2, 3, 4, 5, 6, 5, 25, 28 gigabytes. My goodness. And of course, these can be compressed, but that requires a lot of compute power to run. So just keep that in mind, that the more parameters a model has, generally, the better it performs, but that is a trade-off for compute that you require. So to run this model in production would take a fair bit more setup than running our 67 million parameter model. Now, let's keep going through our training steps. We're going to continue this on in the next video. We've got our model, we've discussed its parameters, and we're going to start moving towards this step in the next one. So if you want to jump ahead and go through the example notebook and try it out yourself, please do. Otherwise, I'll see you in the next video. Welcome back. Now, we've counted the parameters in our model, and we know that in the modern era of deep learning, 67 million parameters is not that large, but as I mentioned, a small model can perform incredibly well with specific data, which is what we're going to be going for. Now, let's create a folder or a directory for saving models. So we're eventually going to save our model to the Hugging Face hub. So if we look at my profile, we'll have something like this. This is what our model spoiler. We're going to work towards saving it to here. But for now, I'm going to save it to Google Colab so that if you didn't want to upload it to Hugging Face, you still have a way to save it locally. And if you're working on your local machine, you could save it to a folder on your local machine as well. So create model output directory. So we'll go from path lib import path, and then create models dir. So models dir, we'll call it, or actually models dir, how about we call it that? Path, we'll just make it generically called models. So for all future models, we can store it in a models folder, and models dir, we'll call mkdir exist, okay. So this means that if it exists already, it's okay to proceed. We'll create it anyway. And then we'll go create model save name. We'll go model save name equals learn HF. So this is learn Hugging Face, so we know that the model. Now you can name it however you want, but I'm going to call mine food not food text classifier Distilbert base uncased. Now these names can get quite verbose. I like to include a fair bit of information in the name whenever I can. You can also update the description here on the README on the model file. Once we create it and upload it to the Hugging Face hub, there's a README there, but I'll let you explore that on your own. If you want to have a look at a naming convention, the TIM library on Hugging Face does a fair bit of naming convention here. So you've got the model name and then some information following it depending on its training setup. So this is specific to the TIM library. For your own projects, you can decide how you want to name your models and whatnot. So if we go back, let's continue on, and we're going to create the model save path. We will go model save dir equals path, models dir, and then model save name. So we'll combine those, and then we'll go model save dir. What does that come out as? Beautiful. Models, and it's now going to save here. Do we get a file over in Google Colab? Yes, we do, but we don't have anything in there yet because we haven't saved it just yet. And give me 1 second. I'm just going to make sure that this model is using the same name as here, so there's no typos. I'm going to copy that. Otherwise, I'm going to duplicate the same model on my profile. There we go. And of course, you can call your own one the same thing. If you ever see my username, just remember to replace it with your own, but we don't have to use the username here because we're only saving it locally. Beautiful. Now, in the next video, let's continue on with our training process. We've got a folder to save models. Let's copy this down here, and we'll continue on with this in the next video. I'll see you there. Welcome back. We've now got a path to save our model to, so we can keep going with our training steps here. I'm just going to put this tick over there. We've created and pre-processed the data. We've defined the model we'd like to use. Now it's time to define training arguments for our model. Now I'm going to put a note here. These are also known as hyperparameters. Parameters. So equals settings on your model that you can adjust. And then parameters equal weights / patterns in the model that get updated automatically. So just keep that distinction in mind, that whenever I refer to hyperparameters, these are settings that you can adjust as a developer, an engineer, and parameters are a little bit confusing with having two of the similar words, but we can figure it out. Parameters get adjusted automatically by the model. So hyperparameters, settings that we set, parameters, settings that the model sets for itself. So let's go setting up training arguments. In other words, hyperparameters with training arguments. So we can do this with transformers.trainingArguments. Let's go have a look at the documentation first, hey? I'll copy that, type it in here. We go to the trainer class. So your extra curriculum is to read through this whole documentation for 10 to 15 minutes. There is a lot there, and don't worry, I haven't read through every single line myself either, because there is quite a bit here. But just jump through each of these and read the headings of them. It's very good practice to get involved in the documentation. I only know where to go on the documentation because I've practiced. So the trainer class provides an API feature complete for training in PyTorch. Beautiful. So this abstracts away a lot of the training steps in PyTorch. So if we go to learnpytorch.io, if this way you want to learn, if we go to PyTorch workflow fundamentals, so if we create a training loop in PyTorch, there's a fair few lines of code here, right? PyTorch training loop, PyTorch testing loop, we've got all this. So trainer provides an abstraction away from that to do all that PyTorch steps behind the scenes for us, and we can just write some high-level settings. It's very helpful. So let's, without any further ado, let's not talk about it, but this is, this is what I mean. This is the documentation. We're not going to go through all of these settings. I've just logged a few of them, but there is a lot that you can do here, which is why I've set as an extracurricular to read through this documentation for 10 to 15 minutes, and you might want to revisit it for a couple of days at a time, if you know what I mean. Because a lot to take in one setting. If we go back to our project, I'll show you what we're going to set up. So we have our transformers.trainingArguments. Let's set that up first, actually, so we know what we're working with. So from transformers, import training arguments. And then we're going to set it up. We have a lot of different parameters that we can use. So we'll print where we're saving to, so we know our checkpoint. Info, saving model checkpoints to, and we'll go model save dir. And then we'll create training arguments. So training args equals training arguments, and then we put in a whole bunch of different settings here. Yeah, look at that. So I'll let you go through all of them, but here's the main ones we're going to focus on. The output directory, in other words, where are we going to save our model? The learning rate, so the initial learning rate to use during training. So the learning rate will depend, because we're using transfer learning, we're going to use a relatively smaller learning rate. Now, the ideal learning rate is going to be experimental. So this is probably the most important setting that you can tune of your optimizer. A higher learning rate means that your model is going to take bigger steps to update the weights. A smaller one is going to take smaller steps. So this requires a bit of practice, but you'll get used to that as you start to train more and more models on your custom data sets. The default is pretty good for a lot of data sets, but in our case, because we're a smaller data set, we're going to use something that's a bit higher than the default. The per device training batch size. So this means how many samples our model is going to look at a time. Remember when we discussed parallel computing, that's one of the best things you can do with a GPU is put as many samples as you can onto the GPU at a time. That means, say for example, instead of looking at one sample at a time, our model is going to look at 32 samples at a time. But if we had a larger data set, we might increase this to 128. If we had 20,000 GPUs, we might increase this to 4,000 or 5,000 samples at a time. So again, these settings are all very experimental in nature. 32 is a good place to start with a lot of smaller data set sizes. Per device evaluation size. So remember how we're going to train on the training data set and evaluate on the test data set? This is how many samples to look at when you're evaluating. Training epochs, so how many laps through the data? We're going to do 10 laps through the data, so that means our model is going to look at the data 10 times, all of it, to try and learn patterns. How often do we want to evaluate? How often do we want to save? How many total models do we want to save? Whether we want to use a seed. So the seed is going to flavor the randomness, Machine learning models are random by default. They use controlled randomness to find patterns in data. If we set the seed to 42, our numbers should, and I say should, come out as similar on both sides. So when I write something, it's not going to be completely random if we use the same seed. Load the best model at the end. So our training values may fluctuate during training. So when we set the best model at the end, say for example, on epoch number 7, our model had the best scores. Loading the best model at the end is going to load that model instead of the model that was on epoch 10. Logging strategy. So how often do we want to log the training results? I set these to every epoch, so every lap over the data. That's what I like to use. Of course, there are many different settings in the documentation. So if we go into here, you can see all of the different options. I'll let you read through all of these. This table here is directly copied from here, but I've taken out only the ones that we're going to focus on. I'll leave the extra ones for you to do your own research on. Report to. This is if we're using an external experiment tracker platform, for example, weights and biases. So if we look up weights and biases, I use this platform to track my experiments on machine learning a lot. We're not going to use any external platform. We're just going to track locally, but that's just something to keep in mind where you'd like to save your experiments to somewhere else. Push to the hub at the end. So this is going to automatically save your model to the Hugging Face hub at the end of training. You can set this to true if you like. I'm going to set it to false for now, so that we don't just automatically override our model on the Hugging Face hub. We're going to see how we can push to the hub manually later on. Hub token. Remember right at the start where we set up our Hugging Face token? That's if you wanted to pass it in manually, which I don't recommend. Always best to set it up as an environment variable. So this could be hub token equals your token here, which will look something like HF and then a bunch of different characters. I don't recommend saving it like that. I just recommend putting it as an environment variable, and this will automatically pick that up for you. So that if we keep going, we've got a couple more. We got this hub repo private. So I've set this to false. So that means if we do upload our model to the Hugging Face hub over here, it's going to be a public. So if you go to this URL, you can see it, it's public. But if you wanted to train your own private model for your company, you can set it to private so that only yourself or someone from your organization can see that. So just keep that in mind, that our default setting is to upload our model and it will become public. So with that being said, let's start filling some of these out, hey? There's a fair few, but we got this. So the output dir for our case is going to be model save dir. The learning rate is going to be 001. See how here that just highlighted? The default is about half of ours. So because we've got a small data set, we can set ours a bit higher. If you had a larger data set, you might want to experiment with a smaller learning rate and training for longer. So per device, train, batch, size, we're going to do 32. And per device, eval, batch size equals 32 as well. We're going to use the same thing there. We could code that as a parameter up here. So for example, batch size equals 32, and then we use that batch size down here. And of course, we could change that however we want, but whenever you see parameters that are capitalized like that, it generally means that there's some sort of hyperparameter or setting to use throughout a notebook. And then we're going to set our number of training epochs equals to 10. This is how many laps over the data that our model is going to do. Eval strategy. I'm going to set this to every epoch, so once every lap over the data. But of course, if we go eval strategy, we look for the options there. We can default to no, so no evaluation is done during training. We kind of want that. We want to see how our model is doing on the test set during training. Again, we could do that after training by just evaluating it on the test set, but I like to see it during training. Evaluation is done every eval steps. So instead of just one epoch, we could do it every 100 steps. So that could be 100 samples, that could be something else. I just like it. It's done one lap of the data. Let's see what the model has learned. We go back here, and then we go save strategy equals every epoch. We're going to save a checkpoint of the model. but we're only going to save a maximum of 3 total models. So rather than saving 10 different versions of our model, we're only going to save 3 total. So that'll just clean up our data. Use CPU. I'm going to set that to false. That way this is the default setting. A lot of these are defaults, by the way. Use CPU. So defaults to false. Whether or not to use the CPU. So the reason why we set up a GPU in our Google Colab instance is because GPUs and TPUs are hardware accelerators. They're a lot faster, or generally much, much faster than training on a CPU. So we set that to false, and whatever hardware we're running on, trainer, so this is the trainer class behind the scenes, will use the best available hardware. So in our case, it's going to automatically use our GPU. If you are on a Mac, it might use your MPS chip. And if you're somewhere else, it might use the hardware accelerator that you have available there. Seed, we're going to set to 42. That's the default, so that our results should be similar. If they're not exactly the same on my screen as your screen, don't worry too much. The trend is more important than the exact numbers. Load best model at end is true. Logging strategy. This is how often we want our model to output its performance during training. And then we have report to. So this is, remember, if we want to save our experiments to an external platform, such as weights and biases or many other different platforms, we can do that. But we're just going to save our results locally. And then we can also set up the hub token. I've commented that out because ours already has access to our HF token over here, or if you're running locally, it will pick up your Hugging Face token from there. Push to hub. I've set this to equal true, but I'm going to comment this out as well. So if you want your model to save directly to the Hugging Face hub after training, so this will save it to the Hugging Face hub as soon as training finishes. We're not going to do that because we've already got a model up there. We're going to push it to the hub manually later on, but just keep that in mind. If you wanted to, just in the future, save it directly to Hugging Face, you can do that. And this is going to be when uploading to Hugging Face hub, do you want your repo to be private or public? Default is public. So if you're working in a work environment, just make sure that if you're saving something to the Hugging Face hub, whether it's okay for it to be public or whether you should have that model as private. Holy smokes, let's see if we've got any errors. Probably. Have I got a typo? Oh my gosh, no typos. That's beautiful. Let's check out our training arguments. This is going to be quite long. There we go. So this, I believe, an instance of training arguments. All of those settings. Look at that. Now, again, I'll let you go through the ones that we missed. There's quite a few there, but we have covered some of the main ones, of course. It would take far too long to go through each one, but that's the beauty of extracurriculum, right? So now we have got step 3 has been completed. We've set up our model hyperparameters. So what's next? Well, we need to pass our training arguments, training args, to an instance of transformers.trainer. If you want to try and do that on your own, I highly recommend going and give it a go. Otherwise, I'll see you in the next video and we'll set up our instance of trainer. Welcome back. We're making our way through training a model. And in the last video, we set up our training arguments. These are settings that our trainer class will use during training. Whoa, there was a lot of training. But let's see our next step in action, hey? I'm going to copy these steps down here. And there's a lot of settings here, so this can take a bit of practice, but nothing that we can't handle, right? Setting up an instance of trainer. And I'm going to copy these, turn this into Markdown, Command MM. And we've done step number 3. Beautiful. So now we are up to pass training arguments to an instance of transformers.trainer. So docs for transformers.trainer. And if we go to the trainer class. We'll click on that one and go here. Beautiful. So the trainer class provides an API for feature-complete training in PyTorch. Wonderful. So instead of writing all of the training code by hand, the trainer provides an abstraction on top of that. And it supports distributed training, which means training on multiple GPU/TPU, mixed precision training for NVIDIA and AMD GPUs, and Torch AMT for PyTorch. And of course, trainer goes hand in hand with the TrainingArguments class, which we've already set up. So we have a fair few parameters or settings that we can use for our trainer class. So we've got our model that we're going to pass it in. We've got the arguments that we're going to pass in, which are our TrainingArguments class that we've already set up, our train dataset, and our eval dataset. We've got a tokenizer as well. But with that being said, let's see this in practice. I'll let you read through the documentation here as some extra curriculum. So we'll copy that. And let's now set up an instance of trainer. So from transformers, import trainer. And we'll set up the trainer class, or instance, sorry. And I'm going to call mine trainer, conveniently. And our first parameter here that we're going to pass in is our model, which is, of course, our Distilbert model that hasn't been trained yet. This is so exciting. There we go. We're going to pass that into the trainer. Of course, all of the trainable parameters will be updated during training. Args equals training args. And then the train data set equals, we have to make sure that our trained data set here is, we have data set. We have dataset train 0. Which dataset do we have to make sure that we use? So there's our original dataset, right? But we also have our tokenized dataset. We have to make sure that we pass in the tokenized version of our dataset, because this is what's going to have, our model is going to expect input IDs and an attention mask. So let's put that in there. Our tokenized dataset. Tokenized dataset and our train split there. And then the eval dataset is going to equal our tokenized dataset test. Oh, writing too much text there. And then we're going to have our tokenizer. So our model knows what tokenizer we're using. Tokenizer. Beautiful. We want to combine all of the pieces of the puzzle together, and that's what we're doing with the trainer instance. And then we're going to go compute metrics equals our compute accuracy function, which, if we recall from a previous video, is what we set up before. Computes the accuracy of a model by comparing the predictions and labels. So if we go into our trainer, we have compute metrics. There we go. The function that will be used to compute metrics at evaluation must take eval prediction and return a dictionary string to metric values. Note, when passing training args with batch eval metrics set to true, your compute metrics function must take a Boolean compute result argument. So let's see this in practice, hey? What do we get if we set up our trainer? Beautiful. We've got an instance of transformers trainer.trainer. So what's our next step? So pass training arguments to transform it to an instance of transformer.trainer. We can train the model by calling trainer.train. All right, now it's time to train our first model. Woohoo, this is exciting. I'm going to leave this up to you to give that a try in the next video, and then we're going to do it together, okay? So go ahead and call trainer.train. Maybe you do that here, trainer.train, and see what happens. Hopefully there's no errors, but if there are, we'll fix them together, hey? I'll see you in the next video. Welcome back. We've now set up an instance of the trainer class, and it's time to train our own model. How did you go? Did you try it out for yourself? Well, before we do that, let's just copy this down here so we know that we're making progress. I'm going to copy down here and then save that there. We've now done step 4 and we're up to step 5. Woohoo! So we'll call train the model by calling trainer.train. Okay, you ready to train the model together? In 3, 2, 1, let's do it. No bugs. Damn it. What did we get wrong here? Okay, value error. Predictions and or references don't match the expected format. So the expected format is predictions. It needs to be a D-type int32 references because this is our evaluation function. So this is what we're getting out of the model, input predictions, but it needs it in this format. I see. So what do we need to do? Let's copy this. Input see how these two are different? Let's fix this up, hey? We were so close. That even looked like it was going quite fast. So I wonder if this will work. I'm going to call this input predictions. Let's fix this is a problem with our evaluation function. So NP array, I'm going to call that. Oh, is this not going to work because there's, yes, there's no commas there. That's okay. Maybe we can do it with just 2 samples. Okay. I think we can figure this out. And then we go input references equals NP array. And we want this to be, let's just say it's that. Because that's what it is, right? It's a list of values. Yeah. Okay. So it needs to be in the same format. So let's get our compute function or compute accuracy function down here. This is what's breaking our code. Predictions and or references don't match the expected format. And we can tell that because it's the evaluate function here. And if we go into, what have we got here? Evaluate, yeah, there we go. This function, this line is breaking our code. Let's go find our compute accuracy function. There we go. Okay, let's copy this down here. There's a bug in this. So let's write that and write that. And then if we go, let's compare these two. So compute accuracy. We'll troubleshoot on the fly, hey? Predictions and labels equals, let's pass in a tuple of input predictions and input references. Where does our error come up? There we go. Okay. So that's the expected format. We need to get the argmax of this, the input predictions, because when we're calculating or evaluating predictions, it needs to be apples to apples. So we need to take the maximum value of this, or the index, because so this is, say this is 0, not food, and this is 1. This is the output of our model. It's outputting logits. So we need to convert this into, whichever one is the highest one, is what our model is predicting is the output label, or the most likely. So let's put in a little line here that goes if len predictions.shape. I just want to show you what this means. So we go input predictions, shape, 1, 2. Okay, so let's go if len input predictions dot shape is greater than 2. I want to go input predictions equals np argmax, because we want to take the maximum value here of input predictions and on the first axis. So the first axis means in here, the 1th axis. We'll take that because this is a 0th axis, this one here, these brackets, and this is the 1th axis. 1th or first? Okay, and then we go input predictions. We should get an integer here because we want to compare this to that. What's happened here? If len, does this come out true? Oh, sorry. It's greater than or equal to 2. There we go. Okay, beautiful. Now, let's see if we put this line in our is greater than or equal to 2. We'll get the argmax. So predictions equals np argmax input prediction, just predictions in this case, predictions, axis equals 1. Let's see what comes out here. Beautiful. So we get 0% accuracy because it got it wrong. So it's supposed to be 0. This is the reference, and our model predicted 1. So we got that wrong. That's okay. That's okay. Our model hasn't even completed a whole lap of training yet. So let's see if this fixes our problem. I'm going to put this up above our function. So compute accuracy. We'll fix that. We'll get our trainer class. We'll see if this works. Trainer.train, you ready to train a model? Let's do it. Oh, and by the way, np-argmax returns the index which has the maximum value. So if you want to look up the documentation, numpy argmax. There, returns the indices of the maximum values along a specific axis. I'll put that in here. So need to get the maximum value from the model output, the index, as this is the predicted, or this is the most likely. This is what our model, because it's probabilistic, right? This is what our model is saying is the most likely label according to the model. See np argmax docs. Okay. You ready to train the model again? In 3, 2, 1. No errors. Let's see what we get. Oh, look at that. Oh my gosh. Accuracy is already 1.0. Is that a bug? Our data set is quite small. So the training loss, we want this to be going down. The loss and the validation loss here is a loss is a measure of how wrong your model is. 0 means a perfect model. If it gets exactly the 0, well then maybe our data set isn't large enough and our model is just doing so well. An accuracy of 1.0 means it's getting everything right on the test data set. That is incredible. Now, don't worry too much if your numbers aren't the exact same as mine. We have set the random seed, but if your numbers aren't the exact same as mine, just make sure the trend is going correctly. The accuracy should hopefully be going up and the validation loss should be going down. Again, you might get drastically different results as well if you're using a different data set. If we have the same data set, our numbers, the trend of the numbers should be quite similar, but that is outstanding results. Look at us. We've just trained a text classification model on food, not food, using a completely open source model. So we could download this model right now. Do we have checkpoints over here? We do. We could download this model right now and classify image captions into food, not food. How cool is that? So with that being said, let's have a look at some of these. That was quite quick too. Our data set is quite small though. Let's check out some of these metrics, hey? And how do we do that? Well, maybe we should have saved this to results. I'm going to do that. Results, because it didn't take so long. That way we can inspect it. So I'm going to re-instantiate trainer and just train, get results. So we know what format results is going to come out. Oh, our model is going even better now because we've actually, the numbers are going even more down now because we didn't re-instantiate our model. So we've actually just trained it twice. So we have to come right back up here to re-instantiate our model if we want to get 10 epoch results. We actually just trained our model for 20 epochs. So I'll rerun this, re-instantiate the model, and if we keep going here, we're going to get some errors, aren't we? That's all right. Doesn't hurt going back over what we've done because we have done quite a bit. And so we'll retrain our model. The beauty of having a small data set and using transfer learning is that model training happens quite quickly. There we go. There's the metrics we want. Oh, it never gets boring for me to watch a model's loss go down. So inspect training metrics. Let's do that, hey? So for key value in results, we can access our metrics. So results is up here. Metrics is going to be a dictionary, so we'll access the items from there. I'll just show you what that looks like. Results.metrics. This is the results from our model. We get some training stats there, and we're going to go print. We'll print this out nicely, hey? Key and value. Well, not really. It's not too much different than just printing out the dictionary, isn't it, Daniel? Wonderful. So train runtime only took 25 seconds. Training samples per second, 79. You see, even if we upscaled our data set, it would be pretty quick training. Total flops, so FLOS stands for flops or floating point operations. Floating point operations per second. That's all the patterns, all the number crunching that our model is doing, which is a very large number. The training loss is quite low, right? So the lower the loss, the better. And then epochs, we did 10. Wonderful. Okay, so before we go into the next video, let's save our model for later use. So save the model for later use, because we want to make sure that if we were to move on to another project, if we were working locally, the caveat here is we are saving to Google Colab. So let me just write this down. Note, if you are saving a model to Google Colab, note that it will disappear from your Colab instance when it disconnects, right? So keep that in mind. We're going to save our model now, but it's going to go over here. But if we disconnect from Google Colab, it's going to be deleted. So we're going to upload it in a second to the Hugging Face hub. But I'll just show you how to save the model. So if you're working locally, this will remain on your file system. So saving model, and because we've set up the model save dir in our training arguments, it's going to save there. So we can call trainer.saveModel, and the output dir is going to be the model save dir. Let's have a look at that. Saving model, there we go. Beautiful. Let's have a look at this. What do we get? Oh, so now look what we've done. We've got the same files. So we've got model.safetensors, which is a file format to store all of our model tensors. This is our model parameters. All right, these are all tensors. So if we have a look at that, all tensors, that's what our model format is. Then it's our tokenizer, config, vocabulary, a whole bunch of stuff. And what does this look like? If we go back to our Distilbert model, we've got all the same files and versions here, except our model tensors now, our patterns in our model have been updated to our custom data set. That is so cool. Now, of course, we got some evaluating to do. So how about in the next few videos, we start to evaluate our model? It looks like with the logging output that it's done pretty well, but of course, we're going to have to test that, aren't we? So I'll see you in the next video. If you want to jump ahead and try and evaluate it yourself, I'd highly encourage that. We've got all the example code here that you can try out for yourself. Otherwise, we'll do it together. I'll see you soon. Welcome back. In the last video, we trained our text classification model, and by the looks of things, it's doing pretty well. We saved it to a local directory so we can use it for later, but now let's jump back into our workflow. We've officially done this. We've done a full fine-tuning of a base model. That's how powerful transfer learning can be. But let's have a look. What's next? We've trained and fine-tuned our model on our custom data. How about we continue to evaluate our model? We may not even need to improve it through experimentation because it's already performing so well, before later on we save it and upload it to the Hugging Face hub. So we'll jump back into our Colab notebook and let's continue to see how we might inspect the model training metrics. So we can get our training history from the trainer class that we instantiated, our instance of it. Get training history. We can get this by going to trainer history all, and this is going to be trainer.state.log history. And then we can also get the trainer history metrics equals trainer history all, and then we'll get everything except the last one. And I'll show you why that is, because let me just show you the trainer history all and the trainer history metrics. So we don't actually need this one down here, the train runtime. That's what we've already got. We've already got that stored up here in results. So just if we get the trainer history metrics, one thing at a time, Daniel, come on. There we go. Yeah, so we can see here that we've got evaluation accuracy and it's interspersed with the training loss. So what we can do is we can write a little bit of a filter to filter out the training epochs from evaluation epochs. So there we go, yeah, loss, this is training loss, and then we have eval loss, eval accuracy. So what we might do is get the trainer history training time equals trainer history all, and this is the last one. And then we can view the first three. So trainer history metrics. Remind ourselves of what that looks like. Beautiful. So let's get rid of that. What we might do is write a little for loop to extract the eval metrics and the training metrics. So how about we start by importing pretrained, pprint from Python, so we can print out a dictionary later on. But let's extract, we'll put it into a list, hey? Extract eval and training metrics. We'll go trainer history training set equals empty list, and then trainer history eval set empty list, and then we're going to loop through our metrics. So we'll go for item in trainer history metrics. Let's go item keys equals list item dot keys, and then we'll print the item keys just to see what that looks like. Beautiful. So what we might do is, yeah, these are the eval options. So if any of the keys have the word eval in them, we should append them to our training history eval list. And if they don't have the word eval, they can go to the training set. So let's write a little if clause there. So if any eval, so this is going to check if any of these conditions is true. In item, for item, in item keys. And I'm going to go print true. Let's see what this looks like. True, 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 true. And then we should get that interspersed with else print false. Beautiful. So training epoch, eval epoch, training epoch, eval epoch. So we can now append the eval set, append the target item, and then this is for trainer history training set. Let's append the current item, and let's go show the first from each. From each, and I'm going to go print, and we go first item in training set, and then we'll go preprint dot pprint because it's going to be a dictionary item, right? And I want to get the trainer history training set. Maybe I'll get the first two. I know that's ignoring the statement above. First two items in eval metrics, eval epochs. Beautiful. Pprint dot pprint. Let's have a look. Trainer history, we want eval set. Get the first two. Let's see what this looks like. Wonderful. Might get a new line there so we get some separation. Oh, excuse me. So we've got epoch 1, and we can see that the loss goes down from epoch 1 to epoch 2. That's wonderful. That's exactly what we want. And same thing on the evaluation set is that the eval loss goes down here. How about we turn these into a data frame, and then we can plot them with matplotlib to have a look at our loss curves. So maybe we put it here, taking a look at the loss curves. So loss curves equals good visualization of your model's performance over time. And so ideally, loss curves will trend downwards. See more here. So if we Google loss curves, interpreting loss curves, yeah, this is a good resource. Oh, this course is out of date. We'll remove it in July 2024. Well, it's August 2024 for me at the moment. Well, okay. Maybe I need to create my own machine learning website. Loss curves. Let's have a look here. Do we have a good piece of information here? Accuracy, learning curves. Maybe we just go images, loss curves. Images. Okay, there we go. We want the loss curves to go down. Okay, rather than looking for resources, let's just look at our own loss curves. How about we do that? See more here. Well, if the Google website still works, we'll put that one there. But otherwise, I might just make my own website for this later on. Okay, we'll create a pandas data frame for the training and evaluation metrics. So trainer history, training df equals pd.dataframe, and we're going to put in trainer history, training set. That's what we want. And then we want trainer history eval df equals pd.dataframe and trainer history. We'll put the eval set in here. Wonderful. Now let's have a look at the trainer history training df. We'll inspect that, hey? Oh wow, that actually worked even though I had a space there. That was cool. Okay, beautiful. So this is just another version of what we have above here. But this time we've got it in our own structured data format. So we will now be able to make a plot using both of these. So plot the loss curves. We'll bring in our trusty matplotlib. So import matplotlib.pyplot as plt. Beautiful. We're going to set up a figure here. We'll put the figure size to 10:6, one of my favorite dimensions. Good, nice rectangle. And we'll have plt.plot because the default is to plot a line graph. And we'll go trainer history, training df, and then epoch, right? So it's going to be this column here. And then we also have this one here. That'll be our next plot. So we want to put loss versus epoch. So we can go trainer, this should be. Might copy that over here. I'm going to put loss, and then I'm going to label it with training loss. Beautiful. Now I'm going to go plt.plot. I'm going to go trainer history eval df, and I'm going to go epoch, and then I'm going to go trainer history eval df loss, and then we'll go label equals eval loss. Beautiful. So just remember that the evaluation data set is the test data set. Our model has never seen that data during training, only to predict on. So we're going to go plt.xlabel. We'll set that up with epoch. And, oh, have I made a typo here? Oh, train df. Excuse me. And this should be OR. There we go. plt.ylabel. We're going to put in loss there. And then we're going to go plt.title. And this is going to be text classification, fine-tuning, distill BERT, training, and evaluation loss over time. And then we can get a legend in there. And then we'll show the plot. Let's have a look at this. What does this look like? Oh no, we got an error. Loss. What's wrong here? Oh, excuse me. This should be eval loss because it's the eval df. That makes sense. Wonderful. Now, they are some of the best loss curves that you can ever see. It starts up not even that high, and then it gradually goes down. So this is a good sign. So, and they sort of kiss towards the end. That's what the ideal setup is. If our eval loss was much higher than our training loss, it would mean that our model is overfitting. So I wonder if I've got that in here, overfitting. No, I have that in the glossary, maybe. Otherwise, I'll link you to a good resource for underfitting and overfitting. Overfitting. Yeah, here we go. Loss value. Now, the glossary isn't that tidy, but I'll explain what it is. So, measure of how wrong, this is the loss. Measure of how wrong your model is by a given metric. A perfect model will have a loss value of 0. It is able to predict the data perfectly, though it is highly unlikely to be exactly 0 unless you've got quite a small data set like us. If the loss on the training set is lower than the loss on the test set, the model is likely overfitting. So this means it's performing better on the training set and it's memorizing the training set rather than learning generalizable patterns to unseen data. So to fix that, we can introduce more regularization or more data, so we can have a larger data set. So if our model loss is not going down, we may need to introduce more learning capacity, more data, more parameters in the model, or longer training. So machine learning in general is a constant battle between overfitting and underfitting. So let's look up overfitting and underfitting machine learning. Here we go. What do we have here? Generalization, overfitting. There we go. Yeah, this is a pretty good article. I've read through this one before. Do we have overfitting on Wikipedia? Oh, there we go. Beautiful. So there's some extra curriculum if you'd like to learn more about overfitting and underfitting, but for now, our model is performing well. So to learn more about overfitting and underfitting, see here. It's always like if our model wasn't performing as well as we'd want, we'd probably do more evaluation. But for now, I'm happy with this, or we'd do more training. I'm happy with this. So I feel like if you're happy with this, if we've got to this stage and we've gone, okay, our model is performing pretty well. Now we might not need to improve it through experimentation. We might as well push it to the Hugging Face Hub so that other people can test it out, other people on our team or other people around the world, right? That's what we're going to do when we build a demo later on. So let's keep pushing forward. In the next video, we're going to save and upload our model to the Hugging Face Hub so that if someone on our team goes, hey, I'm going to try out your model, and we go, well, I've found that it performs pretty well. It's got really low loss, and then they try it out and it doesn't perform that well. Well, then we know we may have to revisit our evaluation step. So in the next video, let's save our model to the Hugging Face Hub. I'll see you there. Welcome back. Now, we've evaluated our model and we've decided that it performs pretty well. And so now let's push it to the Hugging Face Hub. Pushing our model to the Hugging Face Hub. Now, why do this? So we can share our model. Other people can try it out. We can keep a history of different model versions. These are probably three of the main reasons. This one's important too, because if we're training multiple different models through experimentation, we might save them all to Hugging Face off different experiments. So say, for example, because we only have 250 samples, if we wanted to increase that to, say, 100,000 samples, well, we could go our model. So if we wanted to times this by 1,000 to 200,000 training samples, we could go, our model performs this well on 200 samples. How does it perform on even more? So that would be something. Machine learning is an iterative process. So you're constantly trying to improve your model based on new data. So how can we push our model to the Hugging Face Hub? Make sure you've gone through the setup steps here on Google Colab. We've gone through them together, but to write to Hugging Face, we're going to need a Hugging Face token that allows us to write. And if you're on your local machine, you might want to set up the Hugging Face CLI. So this is the documentation for that. But if these two things are set up, let's write this down. To write to Hugging Face, let's go if on Google Colab, set up token with read and write access. And if on local machine, set up Hugging Face CLI. And this one is going to be over here. We've gone through that right at the start of the session, so I might just copy this link here. Beautiful. So let's do it. We now can just save our model to the Hugging Face hub. So model upload URL. So once we call this, actually, let me show you the method. Trainer, do we have push to hub? Yeah, there we go. So push to hub is going to do what it says. Upload the self.model and self.tokenizer to the Hugging Face model hub on the repo self.args model hub ID. So what if we had a look? Is that going to be here? Trainer args hub model ID. Oh, that doesn't return us anything. Well, let's see. Let me write this down. Let me just put this doc in here for you. To save to the Hugging Face hub, we can use the trainer.push to hub method. And then this is over here. Copy that. Always reference the documentation if you can. Beautiful. So that way, if we look at some code and we're not sure what it does, we can look it up in the documentation. Let's just see what it does, hey? Push to hub, and I'm going to put in here a commit message because once we push a model to the hub, it's creating a Git repository or a Git-like repository. If you've used GitHub before, it's very similar to that, but instead we're committing a model here. So uploading food, not food, text classifier model. And then if you wanted to hard code your token, I'm not going to do that here. You can set token here and put your token here. We won't need to do that. And I'd actually recommend not just hard coding your token because it's going to pick it up from there. So you ready? We're going to save this to Hugging Face Hub, and I'll print out a little info message that if it successfully completes, so model successfully uploaded to the Hugging Face Hub with URL and model upload URL. Let's see if this works. This is going to go to my username, of course. Now, it will go to your username if you're logged in correctly. Just want to show you this. Because it's a machine learning cooking show, I've already uploaded a version. So notice all the timestamps here of when these got created. Let's see if this gets updated, hey? Hopefully all the names are the same, so it stays as being the same model. We might get an error here if it's not successfully authenticated. It looks like it is. So it's uploading the model there, model.safetensors. It's going to upload it from over here, where we've saved our model. There we go. Model successfully uploaded to the Hugging Face Hub with that URL. Well, let's open it up. If we refresh this page too, there we go, less than a minute ago. How cool is that? Our model is officially on the Hugging Face Hub. Oh my goodness. So if you go to your username / that, and you could actually share that with someone else now, and if they come to it, well, there's your model. How cool is that? If you wanted to, you could jump in here and edit the README file so you can put in some description and all that sort of stuff. So it's someone, oh, there's our training results automatically logged for us. So if someone else came to have a look at what this model does, they can try it out. But rather than do that, write it in here, you could also just try it out directly in the Transformers code. How cool is that? So we're going to try that out later on, don't you worry, or you might want to jump ahead and try it out yourself, see how it works. That's really cool. But we can also now use this model in a demo. So this is what we're going to be working towards later on. You could type in here, woohoo! Our model is on the Hugging Face Hub. Now, this should be not food, is it? Not food. Beautiful. That's what we want. So congratulations. You've now uploaded a text classification, a custom model to the Hugging Face Hub that you can now share with someone. If you've created your own model, please share it with me. I'd love to see it. My username is Mr. Dburk all over the internet, including in the Discord chat. If you do get any errors here, I've written some notes in the notebook over here. Let's jump into that, of what might be the case, because I got some errors when I was working with it. So if you get the following errors, 403 forbidden, you may see that you don't have the right access on your token. So make sure to go through the setup steps above. And if you get the 401 client error, you may have to again revalidate. So the main errors that happen here are just token issues. So check that out. But otherwise, we can now use our model directly in transformers. I think it's now time to make and evaluate predictions on the test data. So we're always evaluating our model. We've seen the loss curves. We've saved it to the Hugging Face hub. So now we can start to make some predictions with it. Let's do that together in the next video. I'll see you there. Hello, and welcome back. So we've now successfully uploaded our model to the Hugging Face hub, which is incredible. You should be very proud of your efforts going through here. And now, of course, yours will likely be at your username rather than my username on Hugging Face. But now we've got our model saved. How about we keep going with our workflow? So we've trained our model by calling trainer.train. We've saved our model and to a local machine, and we've pushed it to the Hugging Face hub. Now we're up to evaluating the trained model and by making and expecting predictions on the test data and our own custom data, which is data that isn't even in the test set. So let's write a new headline here and say making and evaluating predictions on the test data. So just want to put a note here that we'll go note, evaluating a model is just as important as training a model. Because if you train a model and it doesn't perform well on your test data, well then that's just as good as having no model, right? So we want to make sure that our model can perform well on data it's never seen before. So we can do this by going perform predictions on the test data. Remember, it hasn't trained on this data, it's only evaluated on this data. And from the metrics we've measured so far, our model seems to be doing quite well on the test data, with the eval loss going down. But now we're going to see some real life predictions. And we can make predictions using the trainer.predict method. So if we look up trainer Hugging Face, we can find the predict method, predict, where is it here? There we go. So predict, and we pass in the test data set. So the data set to run predictions on, if it's a dataset.dataset, and then we're going to get some predictions back. So we've got predictions, label IDs, and metrics. That's what we want to do. So I'm going to copy this link here. So we're going to copy for me. There we go. We can make predictions on the test data using the trainer.predict method. Beautiful. So of course we have to pass in our tokenized dataset. Remember, if a model has been trained on a certain dataset, it has to be evaluated on that same dataset or same formatted dataset, mind you. So this is we want the tokenized dataset. This is the dataset our model has been trained on. And we need to evaluate, of course, on the tokenized test dataset. So just keep that in mind. That's one of the major errors in machine learning, is that your model is predicting on data in a format or of a distribution that it wasn't trained on. So we'll go prediction values equals predictions all dot predictions. And then we'll go prediction metrics equals, so this is going to come from predictions all. That's trainer is going to predict on our tokenized dataset test because it's got the input IDs and the intention mask. And then we can also get the metrics by going predictions all dot metrics. And now let's go, we'll get the metrics, hey? Print info, prediction metrics on the test data. And we'll print out the prediction metrics. Beautiful, look how quick that was. So that's the perk of using a small model, is that predictions happen quite fast. Now, mind you, our data set is only 50 rows, but even if you times this by 5,000, or up to 5,000 rows, or 50,000 rows, it would still be quite fast. And we're going to test this later on when we make some predictions, how fast our model can actually get. So the loss is quite low, and it looks like our model is performing at a 1.0 accuracy. That means it's getting 100% of the rows correct. That is incredible. So that's the power of transfer learning, albeit our data set is quite small, but this model is a really good model for text classification, especially if you train it on your own custom data. So with that being said, we can also get our predictions using PyTorch. And so let's do that in the next video. We'll go inspect these predictions. Predictions all. So we get an output array here of different logit values. So we could turn these into prediction probabilities, and we're going to do that in the next video. And then from the prediction probabilities, we can compare them to the labels. So I'm going to just write here. Next video, we'll go from predicted logits, because that's the output of a neural network, is called logits, the raw output that is, and then we'll turn them into prediction probabilities with torch.softmax. And so really this operation here is just making them human readable, these prediction probabilities. In essence, the higher number is what the model is predicting, but prediction probabilities are going to, I'll show you what they look like in a second. They're going to make them much more understandable to us, to predicted labels. Wonderful. So it looks like our model is doing quite well on our test data. We'll evaluate it on custom data later on. I'll see you in the next video. Welcome back. In the last video, we saw how our model did incredibly well on the test data set, and it worked really fast too. So now we've got some prediction outputs here, and these are in the form of logits. So how about we take them from logits, which is a raw output of the model. I'll just put here, raw output of the model, to prediction probabilities with torch softmax. We use an activation function there, and then we'll get predicted labels. So this is not next video anymore. So I'm going to write a little heading here. Let's get predicted probabilities and evaluate by hand. So behind the scenes, this trainer uses the accuracy function that we created. So let's see if we wanted to just do that by hand on our own, if we wanted to calculate that. How can we do that? We'll import PyTorch, and we'll go from sklearn.metrics, we'll import the accuracy score. So sklearn.metrics has a bunch of implemented metrics, and if we go to the documentation, I want accuracy score. There we go. Metrics accuracy score. So basically we need the y-true label, so the test labels, and our model's predicted labels, and then it's going to give us an accuracy score. This is very similar to many other metrics. Compare the true labels to the predicted labels. So let's go back here, and then we can get our prediction probabilities. So get prediction probabilities with torch softmax. So we'll go pred probs equals torch dot softmax, and then we'll turn our items here. I believe they're a NumPy array, the output. Yeah, array. So let's turn them into a torch tensor. We'll go prediction values. Wait, do we have prediction values? Yes, because I've extracted the predictions here. So if we just go, this is predictions all, and then if we go predictions all dot predictions, that gives us that item there. That's an array. So what we're trying to do with torch softmax is we're trying to put these through the softmax function. So if we look up softmax function, It's got to be this formula here. Essentially what this is going to do, I'm going to write this down and we'll just see it in live action. Hey, can we get number 1 or 0 here? Item 0. So if we go torch.softmax, I'll just keep this up here so we can see the change. This is how I like visualizing things. Visualize the change of them. We need to turn this into a torch.tensor, and we might need to fix the dimensionality here. Torch tensor, do we need the dim here? Dim equals 1. Maybe dim equals 0. Sometimes I have to play around with these things. Yeah, there we go. Okay, beautiful. So what has this done? So it has taken these two values, put it through the softmax function. If you want extra curriculum, I would encourage you to replicate this function from scratch. And if you want an example, we could just say softmax function in raw NumPy with ChatGPT. There we go. That ChatGPT did that for us, but if you want to practice recreating this on your own. But we're using the PyTorch version. There we go. Very similar. So that's what's happened. But what happens is, let's describe it with words. Takes these values in, puts it through this function here, and it might be slightly different to torch.softmax, but same equation on the whole. And then softmax, we'll write it down. Softmax gets all values to be between 0 and 1, right? So this is between 0 and 1, these values, and the total of the values sum to 1. So it squishes them to between 0 and 1, and all the values also now sum to 1. This is what's known as a prediction probability, as in the model is assigning this value to how likely the prediction is given the sample. So in this case, we have 99.99 to the power of e to the negative 1. So this is the equivalent of 0.9939, and it's giving the other one 0.00, this is going to test my scientific notation here, 58, or something like that. Okay, so it's saying that this first option, so the 0 index, is very unlikely. Now, note, these values don't suggest how right the model is, because a model can still have a high prediction probability but be wrong. It's only the amount of probability the model is assigning to a sample. It can still be wrong. I'm just going to write this. This is a very important thing to concept, because sometimes you can look at a prediction probability and go, well, that's how right it is. It's like, no, that's how much the model thinks that it's right. The model, just how right the model is, because a model can have a high prediction probability but still be wrong. And if we look up the meme ML dog versus muffin, I think this is a great one. Yeah, here we go. So how to confuse machine learning. So let's say we built an image classification model to predict the breeds of dogs. We could feed it an image of a muffin, and the model would highly predict that it looks like a Chihuahua, or I'm not sure exactly what this dog breed is. I think it's a Chihuahua, right? So it could say, well, this photo, because I've seen dog images, is going to be assigned 0.99 prediction probability that it's a Chihuahua, even though it's a muffin, right? So the prediction probability is high, but the answer is wrong. So keep that in mind. That's one of my favorite memes. So if we come back here, where were we? We've got our raw logits, model outputs raw logits. I know there's a lot of terminology, but that's just the field of ML. A lot of terminology you're going to come across. Raw logits that get output, then we can turn those logits into, these are much more human readable, but they still represent similar values. We have prediction probabilities, and then we have prediction probabilities can be high, but they don't say, this is just the value the model is assigning of how probable the answer is given my training data. It can still be wrong even with a high prediction probability. So now we're going back to where we were. We want to get the softmax across the entire array that we have. So let's check out our pred probs. There we go. So it looks like our model is quite confident on most of its predictions, right? That's because our data set's quite small and our test data set is very similar to our training data set. So where you'll see lower probabilities assigned is when you'll have like a sample that the model is not quite sure that it has seen before, but we'll test this later on when we put in our own custom data rather than samples from the test set. So we'll get the predicted labels. We're going to go pred labels equals torch.argmax, and we're going to go pred probs equals dim1. So we'll get the argmax, which is the maximum index. So let's just have a look at what pred labels looks like. Beautiful. Now we've got apples to apples comparison, right? If we come back up here, predictions all. Do we have an item in here, which is the labels? Yeah. Label IDs. So this is our test labels. This is the official labels that we uploaded when we put our test data set into our model. So what we want to do is compare these labels to our pred labels, right? And it should be 100% accuracy because that's what we got from the predict method before. So we can get the true labels from there, but we can also get them directly from the data set. Oh, excuse me. Fingers are unaligned on the keyboard. And then we have get the true labels. So true labels, because all evaluation is comparing truth to predictions. So we go here, label, and then we go for, and we're going to go compute predicted labels to true labels. This is our original data set, by the way. We could also use tokenized data set. Why don't we do that? Is that going to give us the same thing? It should. Yeah, there we go. And so we're going to compare prediction labels to true labels and get the test accuracy. Test accuracy equals accuracy score, and then y true equals true labels, and then y pred equals pred labels. And then we can print this out in a nice little output format. Print info, we're going to go test accuracy equals test accuracy times 100, and let's see what we get. Boom, 100% test accuracy. That is incredible. And while we're on the topic of prediction probabilities, I just want to put a little note in here that's quite helpful, and I do quite often, is note, if you want a good evaluation method, make predictions on your entire test data set, then reverse index on the predictions which are wrong but have high prediction probability. You don't actually need to reverse index, actually. You can just index. For example, get the top 100 to top 1000, depending on how big your data set is, and go through all of the examples where the model's prediction had high probability but was incorrect. This often leads to great insights into your data, right? So that means that the model because our model is performing quite well for our given data set. So if we had an example where the model's prediction probability was really high, but the truth label was wrong, we might find that sample is a little bit confusing, or we might actually find that true label is incorrect and our model was correct. So that's model-driven evaluation. Now, we've done some predictions on the test data set. If we wanted to, actually, should we just implement this? Yeah, let's implement that. I'll see you in the next video. You can try to implement this. It won't work too well on our data set because I think all of our prediction probabilities are high, but I just want to show you what it would look like if you were to implement it. So I would probably turn our predictions into a data frame and then inverse on the prediction probabilities. So give that a go, and we'll do it together in the next video. Welcome back. In the last video, we got our prediction. Should be prediction probabilities. Prediction probabilities, and we evaluated our model by hand. That's a really, really helpful skill to be able to do. So now we briefly discussed, let's go exploring our model's prediction probabilities. And then go, it's a very good way to evaluate a model by sorting predictions by prediction probabilities and seeing where the model went wrong. So just keep this in your toolkit for going forward. With our data set, it's going to be a little bit hard because our model didn't get any wrong. We might see this later on when we work on custom samples. So make a data frame of test predictions. And I'm going to go test predictions df equals PD data frame. And then I'm going to put in here, we'll get the text because it's always good to do the text. And this is a step I do on almost all of my data sets. I always go through the predictions and compare them and see how our model is doing. And then we go true label. I'm going to go true labels. And then I'm going to go pred label. This is all from above, by the way. Pred labels, true labels. We can get our tokenized data set. Does that still have the text? Let's have a look. We'll see that because that's where our predictions went. And then we got the pred labels. And then, of course, we got the pred prob, which is going to be, we'll get the maximum value of our pred probs. So if we go here, we'll take the torch max of this. So this one, the maximum, beautiful. So torch.max, and we'll go pred probs. We'll go dim equals 1. And because we're using a data frame, we don't want torch tensors, so we'll take the values from that. Is that giving me an error? I don't think that's an error. We'll find out. Too fast for Google Colab. Beautiful. That's exactly what we want, right? So here, of course, we've got our text, and it seems like our model is doing quite well. It's predicting with high probability food and not food samples, and it looks like they're all correct. So if we wanted to, if our model actually did get some wrong, that is, we could just sort it for examples where the labels don't match up, and then we could sort it by the prediction probability, so highest to lowest. So that would be descending order. That always confuses me, descending versus ascending. I know it shouldn't. I know I should know that by now, but I have to think about it. Let's go the lowest prediction probability because all of ours look high. And go test predictions. This is the power of transfer learning. Because our model has such a good baseline representation of language, we can feed it a few samples and get a really good output, especially with binary comparisons. That's a really important problem. So ascending equals true, and we're going to go head is 10. So this is going to start, that's the lowest prediction probability. Set of muffin tins stacked together. To me, that is not necessarily about food. It is muffin tins, but it's not directly food. So this is, okay, perfect example, right? Is that now we've got a way to explore our data set where it could probably be improved. So this would be something we'd have to discuss with our team or with ourselves, make the decision whether we want to label samples like this, which are sort of about food, but not entirely. If we wanted just food items, for example, if this was muffin tins with muffins in them, then I would say that's about food. But actually, no, this is saying it's not food. Okay, then that's correct. Wow, our model is actually better than what I was thinking with my head. That's incredible. See, that's also another power of looking at your model's predictions, that your model can actually get so good that it surprises you. So just keep this in mind. If you want to evaluate your test data and you have quite a large test data set, sort it by the ones that it got wrong and then show the samples which have a high prediction probability but were wrong. So just keep that in mind going forward. I think now we've done enough evaluation on the test data. We've seen our model performs really well. How about we perform predictions on custom text, as in text our model has never seen before. Text that we could make up like this, if you know what I mean. So we'll try that over the next few videos. I'll see you soon. Welcome back. We've now made some predictions on the test data. How about we make some predictions on our own custom data? This is one of my favorite parts of training a machine learning model. So we'll write down here, making and inspecting predictions on custom text data. And let's start this off. Actually, I'll make another heading, which is we're going to discussing ways to make predictions. And predictions are also going to be referred to as inference. Just want to write down here, note, whenever you hear the word inference, it means to use a model to make predictions on data. So when we go to our application here, which we're eventually going to build, if I enter some text in here, just let our little app load. Should have already had this preloaded like a good machine learning cooking show. So if I go, hello, my name is Daniel, and I'm building my own ML model for Nutrify. When I click submit, the model is performing inference here. It's making a prediction. So that's what inference is. That's just a common term that you'll hear. And let's set up our model paths, because right now we've got our local, we've got a couple of options. This will make sense in a second. I'll bring it back. So models dot, if we come over to here, we should have models. Yeah, I can copy this path. Copy path. This is for Google Colab. Your path might be different, so just keep that in mind. Models here should be quite a similar name. And then we have Hugging Face model path. And then in my case, I can get the model path by copying that. Remember to change your username for your own model there. So Mr. Dburke / learn HF food, not food, text classifier, distilled uncased. Oh my goodness, try and say that fast 10 times. So we've got two ways to load our model. If we wanted to keep it all locally, we could do it from that. If we're working in another file system and we don't have access to our local model, we can always load it from Hugging Face. So we'll see what this looks like later on. But we're also going to we'll set up our device in a second, but I just want to break this down of what we're going to do. Two main ways to perform inference. So number one will be pipeline mode, is using transformers.pipeline to load our model and perform text classification. So if we look up transformers.pipeline, let's see what we get. Pipelines are very powerful part of the transformers ecosystem. There we go. So pipeline text classification, that's exactly what we want to do. So the pipeline abstraction, it makes it so that you can perform predictions very quick with a couple of lines of code. So let's put this over here. We're going to see this in practice. See the docs for that. But we can also do PyTorch mode. And they both have their pros and cons. Pipeline is very quick to get up and running. PyTorch mode gives you a little bit more flexibility, but it takes a little bit longer to get up and running. Not much longer though. So we're going to use using a combination of transformers.auto tokenizer. So remember, we can create an auto tokenizer to turn our data into numbers using our model path. So we'll take text, turn it into numbers with auto tokenizer, and then we'll use transformers auto model for sequence classification. So that's for text classification or any kind of sequence, and passing each our target model name. So we'll see how both of these work throughout this section here. And a little tidbit for each mode. So each mode supports predictions one at a time, fast, but can be slower with many samples. And 2, batches of predictions at a time, faster, but up to a point. E.g., say you predict on 32 samples at a time. This may be way faster than 1 at a time, but if you go to 128 at a time, a batch size of 128, you may not see many more speed ups. So that's just a tidbit there. Generally, when you can make predictions or inference on batches, you should, because it's much faster. We're going to see that later on. Predictions one at a time, however, you may need to, for example, if you had a comment system, you may need to just make a prediction on that one comment. But if you had a database and you needed to predict over that whole database, use batches. Let me just write this down. Helpful for, say, a comment system, and comments happen sporadically, to predict whether the comment was spam or not. So that's binary text classification, right? And then you'll also have batches, helpful for when you have a large static database or many samples coming in at once. So if you had a live chat, you might want to make predictions one at a time as they come in. But if you are a large company and you have, say, 1 million articles in your database or emails, and you want to run predictions on that, best to use batches, because as we'll see, that's going to be much quicker. So let's prepare ourselves. I'm keeping this test sentence for later on. Test custom sentence, and we can customize that to whatever we want. Let's set up our device for making predictions. So note, generally, the faster the hardware accelerator, the faster the predictions. For example, if you have a dedicated GPU, you should use it over CPU. So here's where we'll set up some device agnostic code. So if we're working, whatever environment we're working in, we'll set this up for, let's go an NVIDIA GPU, which we are lucky to have access to thanks to Google Colab. If you're working on a Mac, you might want to use the Mac GPU because transformers can take advantage of that. And then if we don't have access to an NVIDIA GPU or a Mac GPU, we'll default to using the CPU. So, which will likely be the slowest option there on our model. And again, this will be depending on the model you use. Some models are optimized for certain devices. In our case, our model is optimized for CUDA, which is an NVIDIA GPU. So we can check for Mac backends by going MPS is available, and Torch backends.mps. So MPS stands for Metal Performance Shaders. This is part of PyTorch. So PyTorch MPS. I'll leave this documentation here if you'd like to explore that a little bit more. So we'll go there and we'll set the device equals torch.device MPS, and then else we'll fall back to CPU, torch.device CPU, and then we'll return the device. So if we set our device, set device is print info using device is going to be our device. What do we get? We should get CUDA. Beautiful. Okay, so we've set it up. We've discussed some options here for making inference. We've set up our local path and our Hugging Face path. We can use either of those. We can use either of those, and we can use either of these. So we've got some options to go through. We're going to work our way through each of them. So in the next video, how about we use the pipeline with our custom model? So I'll see you there. Welcome back. In the last video, we discussed options for making inference, particularly using pipeline mode with transformers.pipeline and PyTorch mode with a combination of auto tokenizer and auto model for sequence classification. And we can make predictions one at a time and in batches. So each of those have their pros and cons. Let's now move on to making predictions with pipeline mode. See the docs here. So we've already put the documentation there. We'll put it again. Why not? So we'll go into here and we can pass in just a single text string to say what kind of pipeline we'd like to use. However, if we'd like to use our own custom model, we can also pass in the model parameter. Now, if we come down here to transformers.pipeline, we've got a task here. There are many tasks that you can do, but we're going to be focused on text classification. There's image classification, image to text. Is there text to image? Text classification, zero shot. So a bunch of different pipelines. I'll let you explore those as extracurricular. But for now, let's write up some code. And if you want to read, there's the device we can set. We've set that with our function above, set device. If you want to read through this, I'd highly recommend doing so because pipeline comes in very handy with the Hugging Face Transformers ecosystem. So to start off with pipeline, we'll import torch. And from transformers, import pipeline. We're going to set the batch size. So this is where pipeline enables one at a time or batch size. So we can set the batch size to default to 32. Reminder, prediction speed often increases with higher batch size, e.g. 1 to 32. But can saturate at even higher batch sizes. Now, I say 32 as an arbitrary number. You may set a batch size of 4 and your model gets the best prediction speed it's going to get. You may set a prediction size of 128 and your model gets the best prediction speed it's going to get. So this is an experimental hyperparameter. I just use 32 to begin with because it's a good middle ground in the world of machine learning. It's kind of funny how certain numbers show up a lot. So create an instance of transformers.pipeline. Sorry, and of course, this will depend on your hardware size too. So just keep that in mind. Our GPU, I think, has 16 gigabytes of memory. NVIDIA SMI, or 23 gigabytes of memory. That's cool. I didn't know that. 24 gigabytes, thereabouts. That's really cool. I didn't know the L4 had that. So let's go food, not food classifier. And this is where our pipeline is going to come in handy because we can just go task equals text classification, which is what we want to do. We could just leave it like that. The pipeline would work just like that. But we're going to work on our own custom problem. So local model path, we're going to use that first. The device, we're going to set to the device. The top K, which is going to be the number of samples that get output by our model. We'll see what that looks like later on. And batch size equals batch size. These are the main ones we have to put out there. So now it's going to use our local model path, which is above. Beautiful. A batch size of 32 and text classification, and it's going to output one prediction. So let's see what our pipeline looks like, eh? Food, not food classifier. Wonderful. There we go. We've got a pipeline set up. Now let's see how we can use it. So we've got our sample. There we go. Might change this to, yeah, that'll do. Then we can just go food, not food, classifier. And we will put in our test custom sentence and see what happens. Not food. Beautiful. Now, if we change this to, for breakfast, I had rice cakes and fish. Wow, that works so quick. Oh, that's so cool. And then we can put in whatever other sentence we want here. My local coffee shop has the best croissants. Not food. Wow. See the score, the prediction probability changes? Now, this is a good one here actually, because this is the power of testing out with custom samples. This caption is it is about food, but it's not directly about a food item, as in the photo wouldn't necessarily have food in it, if that makes sense. So what if we did a plate of croissants at a coffee shop? Not food. Wow. Okay, so this is an example of where we may need more data. Food. Wow, that's okay. So we've explored, this is the reason why we make predictions in our custom test set, or custom data. So now we can, if we wanted to, increase the data set with examples like that. So let's keep pushing forward. How about we try test not food sentence? One of my favorites is a yellow tractor driving over a hill. We go food, not food classifier on our test, not food sentence. Not food. Beautiful. That's exactly what we want. And here, how about we go this? I have a deep learning computer and I love it. That's not food. Wonderful. Or something that really wasn't food. Like if we were filtering a large image data set, is a 2007 Subaru Impreza, right? If we were filtering an internet-sized data set, wonderful. That's going to be a car. We don't want that to output that as food. So that's what we'd use our food, not food classifier for, right? Like if we have a data set like Koyo 700 mil Hugging Face. This is a collection of 700 million images online. Data set. There we go, Koyo data set. So, large-scale image data set with captions. So if we wanted to classify this text, is this image about food? Right, these are images and captions from the internet. If we wanted to filter this data set for only food images, what do we get from that? Not food. Beautiful. That's exactly what we'd want, right? So let's keep going. We can also use our pipeline. I want to show you how this works. Use pipeline with a model from Hugging Face. So if we delete our pipeline, del stands for delete in Python. Do we have a pipeline? No, we don't. So let's set up our food, not food classifier. Food, not food classifier is going to equal pipeline. We'll set the task equal to text classification. This time we're going to set the model to the Hugging Face model path. Just remember this, you'll need to change your username there from my username to your username, or you can use my model, it doesn't matter. But if you want to use the own model that you've trained, I'd recommend changing your username there. Device, top K, we're just setting, all we're changing is the model that we're using, or the source of where the model is, because it is the same model. And then if we do food, not food classifier, is this going to work on our test, not food sentence? What do we get? Pipeline is not defined. Oh, excuse me. From transformers import pipeline. Oh, we didn't need to do that, did we? We didn't need to delete our pipeline. We needed to delete our food, not food classifier. We've already deleted that, haven't we? Okay. Do we have the food, not food classifier? No, we don't. That's exactly what we want. Now we'll create this from Hugging Face. See, it's going to download the model from Hugging Face. Yes. Oh, well, don't you love it when things come together? So this is our custom model trained on our custom data set and not food with the same value as our local model path. That is so cool. Okay, let's see in the next video how we can, so this is a prediction at one at a time, right? We've done one at a time. And that's pretty quick, right? Almost instant predictions one at a time. Let's see in the next video how we can make predictions on batches at a time. And if you want a little challenge, I would suggest see how you can make predictions with this pipeline here on a batch of samples. And a little tidbit, the batch of samples should be a list of text. So give that a try, and I'll see you in the next video. Welcome back. In the last video, we used the transformers.pipeline abstraction to make predictions really quickly. And you'll notice that when we pass our pipeline, our Hugging Face model path, it downloads all of our files from Hugging Face. So we've got the config, the model, the tokenizer, the vocabulary, the tokenizer JSON. So behind the scenes, when we pass in our test not food sentence, pipeline will tokenize it for us and then pass it to our model and just return the output predictions. So, and by the way, if we wanted to swap this to 2, we'd get the prediction probabilities for both of our samples. So that's really cool. We could just get the top one. Now, let's go. We will go making multiple predictions at the same time with batch prediction. You may have already tried this, but let's try it together. So if we come over to the text classification with Hugging Face documentation, well, not documentation, this is just our example notebook, learnhuggingface.com, and I've got a list of sentences already prepared, like all good cooking shows. And so sentences, now I'll show you how easy it is. You might have already done this, food not food classifier, to make predictions multiple at a time. We just do it like that, and there we go. Done. We just pass a list into pipeline. How cool is that? So these are some sentences that again were generated, and then I added some of my own. I'm not sure, like ChatGPT just generated this on the fly. I don't know where it got that from, but hey, if it's read the whole internet, maybe it's found out who I am. I'm joking. We have here, this is a nice confusing one. So a beautiful array of fake wax foods. I wanted to see if it'd identify fake foods as food. And if we see here, it's not food. It said that Daniel Burke is really cool. That's not about food, is it? But it says that this one is about food. So that's a thing that we'll have to experiment with and go, if we're building this model, what are we going to classify as text? If this is talking about fake foods, so it is kind of about foods, and shokuin sempuru, if we look this up, it's actually really cool, a little aside, is a food model, but it's made of wax. So that's just something to think about, right? Is this food? I would say no, it's not edible food, but it is still kind of about food, right? So this is why we always evaluate on our own custom data and we try and test it out. But if we want to create some new sentences like this, let's go to Meta with Llama 3.1 405B. Can you generate a Python list of image captions about food and not food like the following? Make a list of 10 examples of each food and not food. Let's see if this works. If not, we'll go to another one. Food captions, beautiful. Okay, let's try this out. Food captions, is this always going to be about food? Food captions and food, not food classifier. All about food, beautiful. Our model does incredibly well there. And then if we go there, not food captions. Again, this is not a perfect demo, but it's close enough. Food, not food classifier. This is the power of testing with synthetic data. Not food captions. How does our model go? Not food, not food, not food. So our model does pretty well, even on samples that are out in the wild, right? Or generated samples. We did, how about we go, can you make 10 confusing image captions that might be about food, but really aren't? Let's see if we can confuse our model. Oh, that's cool. We'll bring these in. Confusing captions. Food, not food. Classifier. Let's test this out. Oh, there we go. We've confused our model. So this is an example of where we can improve our model. So not food. So the new project was a recipe for disaster. The team's strategy was a bit of a stretch, like trying to make a souffle. Okay, well that's kind of, it is, the food name is in there. Then if we got food here, the plot twist was the icing on the cake. Well, it's got icing on the cake there, but I would say that's not about food. Then we have not food. The city's traffic was a real meat grinder. Not food. The new policy was a tough pill to swallow. That's not food. And then we have, what else was down here? Food. So this one, the politician's speech was a lot of empty calories. Oh, this is great. The new idea was a bit of a lemon. Food. Okay, so this is something that we'd have to consider. So whereas an LLM like Llama 3.1405B is very, very capable, the difference between our model is that it runs very fast and we can deploy it anywhere. So, and we don't have to make an API call. Like this could just use a file that's on our machine. So something to consider. And as an extension, I would highly recommend, if you want to improve our model, you could create more samples where the model gets it wrong, and then add that to the training data set, retrain the model, and see how it goes after there. So with this newfound superpower of being able to perform inference over multiple samples at a time, let's now, in the next section, time our model making predictions. We've only done it on 10 samples here, and it's really fast. How about we step it up a notch and pretend like we have a data set that's thousands of samples? I'll see you in the next video. Welcome back. Now, in the last video, we made predictions in batches. This is a superpower with machine learning models. It's usually a lot quicker. So let's test that, hey? We only did 10 samples at a time, but what if we had way more than that? So time our model across larger sample sizes. Let's see how fast our model can get. So I'm going to import time so we can time it, and I'm going to create 1,000 sentences. And I can just do that by going sentences 1,000 equals our sentences of 10 times 100. And then if I go len sentences 1,000, what do we get? Beautiful. And remember, sentences looks like this. Okay, so we've just got 1,000 of that. Our list is much bigger now. So 1,000 samples. How long will it take for our model to make predictions on 1,000 samples? And if we really truly wanted to make this a good test, like these would all be random samples, but hey, we'll do what we can. This is going to be a good proxy. So time how long it takes to make predictions on all sentences. Now this is going to be one at a time. We start with this as our baseline. So print info number of sentences is going to be len sentences. We already know this actually. Sentences 1,000, and then we'll go for sentence in sentences 1,000. Let's go make a prediction. Oh, we actually have to start the time actually. Start time equals time.time. Beautiful. And then we'll go food, not food classifier on our target sentence. And then we can go end time one at a time equals time. Actually, I might change this to start time one at a time. Beautiful. A little bit of a mouthful then, But now we can just go print info total time for making predictions. I might just do this, total time 1 at a time equals, we're just going to copy these variables, aren't I? End and start on len is going to be this needs to be in squigglies S, and then we'll print the average time per sentence, hey? Info av time per prediction is going to be av time per pred equals this divided by len sentences 1,000. Beautiful. Then we put the average time per pred down there and a little S after that. Let's see how this goes. It gives us a little heads up. You seem to be using pipelines sequentially on GPU, so that's one at a time. In order to maximize efficiency, please use a data set. So we have 1,000 total sentences, beautiful. And the total time making predictions on 1,000 sentences, or maybe do here, 1,000 samples, is 6.2 seconds. So 6.26, but per prediction is 0.006. So that's pretty fast, right? 1,000 samples in 6 seconds. That's a lot faster than what I could make predictions on it, right? But how about we step it up a notch? Why don't we use pipeline now and in batch mode? So that was one at a time, on 1,000 samples, one at a time. Average time per prediction, one at a time. So let's now do it. Let's now use pipeline in batches. So we get about 6.3 seconds, thereabouts, for 1,000 samples, or 0.006364 per sentence. Let's create a bunch of different ranges. So for I in 10, 100, 1,000, and then even 10,000. Oh my goodness. And we're going to go sentences big equals sentences times I. And we'll go print info number of sentences equals len sentences big. We go start time equals time.time. And then we're going to go predict on all sentences in batch mode. So this is where we're going to use our pipeline. So this is going to be, sentences big is going to be just a list of sentences. So for example, if we do food not food classifier on, we just pass it in the list, right? I'll comment that out. We just see what it looks like. There we go. So it's going to start predicting on 100 sentences, 10,000 sentences. Oh, what do we get wrong here? There we go. 100 sentences, 1,000 sentences, 10,000 sentences, 100,000 sentences. Can we do it? Yes, we can. Let's go end time equals time.time. Wonderful. And now we're going to go, let's calculate total time per all sentences. Batch mode equals end time minus start time. And go av time per sentence, and batch mode will be this big one divided by length of sentences big. Okay, and then we can print this out. Print, you know I love printing out little info things here. So inference time for len sentences big, and then we go sentences is going to be, let's round it. We don't have to round it, but I might round it to 6 decimal places so we don't get a huge output here. And then we'll go print. I might put batch mode there as well. Info, we're going to go av inference time per sentence will be av time per sentence batch mode. I might round this one as well. Round, maybe that could go to 8 decimal places. Let's see what this comes out as, hey? And then we'll print that. Okay, pipeline mode. Okay, that was extremely quick. Now 10,000 sentences. Here we go. 10,000 sentences only took 5 seconds versus up here 1,000 samples. So we're getting a 10x improvement in speed there. Isn't that crazy? There's one extra zero. Now we're doing 100,000 sentences. Hopefully it doesn't take too long and we can do this just in live mode. But this is not far-fetched, right? If you have a large database that you've been working at a company, or there's another company that has hundreds of thousands of records, you may have to perform predictions on 1 million plus, right? So 100,000 is a good example of what we can do. We'll leave that run for a second, but just compare here. This is the difference between batch mode. So we did 10,000 sentences in batch mode faster than what we could do one at a time on 1,000 samples. That is incredible. And so this is going to finish up. There we go. So 100,000 sentences in 51 seconds. Isn't that incredible? That is absolutely incredible. 100,000 image captions in under a minute. That is so cool. That is the power of using a small model, right? And a power of fine tuning. And we know that they do pretty well on test data. We did see with some confusing samples it can get a little bit wrong, but that's where we could start to sample, show me the ones with lower prediction probability, you know? And now let's, I've got another comparison. I've actually done this in the example notebook. We've got a little table here across even more sentences. So I've got the range here. This is on my, an NVIDIA L4 GPU. So the same GPU that I'm using in Google Colab, right? I didn't do it one at a time for 100,000 in the notebook because it was going to take too long. So one at a time, right? 605 seconds, which is still actually quite quick for 100,000 samples. But if we can get it 10x faster, 49 seconds with 100,000 samples in batch mode, why wouldn't we use batch mode? So just think about that. If you need to do predictions one at a time, it's going to be quite quick. Some scenarios require that. But if you need to predict it on a large data set, try to use batch mode. Now, with that being said, let's go and see how we can make some predictions using PyTorch. If you want to jump ahead and try that out, give that a go. Otherwise, maybe keep playing around with pipeline and see how fast you can get it, or see with different batch sizes. Because remember, we've only used batch size 32. So maybe you write some for loop code to use a different batch size in this loop and see how that compares. All right, I'll see you in the next video. Welcome back. In the last video, we saw how fast our predictions can be made with pipeline mode, and it is quite fast. But now we've also discussed that we can make predictions with PyTorch. So making predictions with PyTorch. If you're just after straightforward predictions, pipeline is probably where you want to go. But if you want to a bit more flexibility around the predictions that you're making, you'll probably use PyTorch. So let's go from transformers, import. Actually, I'll just write the steps here. Steps with PyTorch. Predictions will be 1, create the tokenizer with auto tokenizer. So pipeline handles these steps behind the scenes. 2, create the model with auto model, which is going to be, in our case, auto model for sequence classification, because we're doing text classification. 3, tokenize text with 1. 4, make prediction with 2. 5, format prediction. So see how there's a few different steps here? It does require a few more steps, but that just means that we can customize each of these steps along the way instead of with pipeline, which kind of bundles these all together. So auto tokenizer, we'll import that and we'll set up the model path. Now, this can be a local model path or a Hugging Face model path. Remember just to change it to your own model path if you want. Your own username if you want to use your model, or you can use the one from my Hugging Face repo. And we're going to create an example to predict on. So we'll do some sample food text, why not? Equals a delicious photo of a plate of scrambled eggs, toast, and bacon. Right, one of my favorite breakfast foods. And now we can prepare the tokenizer. So we'll do step 1 up here. And these don't have to necessarily go in order, the first 4 steps. The first 3. We can just do tokenizer, then tokenize the text, and then create the model, then do the prediction. But let's prepare our tokenizer. It's going to be auto tokenizer from pre-trained. And then we can pass in here pre-trained model name or path equals our model path from above. And then we can go inputs, which is the inputs to our model, is going to be tokenizer, sample food text. And then we're going to go return tensors. So this is because PyTorch needs tensors. I think it's PT by default, by the way, this return tensors. Let's just see what this comes out with actually. Inputs. There we go. Okay, beautiful. Now, if we set this to return tensors, what do we get? PT is for PyTorch. PT stands for PyTorch. Okay, because PyTorch is going to want tensors. So if you want it to default to output PyTorch, just pass in return tensors PT, and then see here, we now get some tensors as our input there. So we've got some input IDs. Our text has been tokenized. Now let's create our model. So we can go from transformers, import auto model for sequence classification. And we're going to load our text classification model. Model equals auto model for sequence classification. And then we're going to go from pre-trained. And then we'll put in the pre-trained model name or path. We don't have to type this all out, but I just like being verbose so we get used to the parameters to begin with. And then if we have a look at our model, what do we get? Beautiful. We get our Distilbert for sequence classification. You notice how it didn't have to download anything from Hugging Face from our model path here? That's because if you have restarted your Google Colab instance, it will have to re-download it. But that's because up here, we've already downloaded the model. So behind the scenes, Hugging Face will, if you've downloaded a model and saved it to your file system, wherever you're operating, Hugging Face will try and find an existing version of that model rather than downloading a new one. If the model has been updated, it will download the new one. But if you've already got it, it won't download it. So there's our model, all ready to go, all shiny, freshly trained. So to make some predictions, we can use Torch. So import Torch. I think we've already done that though, but we'll just do it anyway. So with Torch no grad, we can also use with torch.inference mode. This is going to just say, hey, PyTorch, don't use gradients. We don't need to update gradients. We might put our model into eval mode too, by the way. So that's going to switch off all the gradient tracking in PyTorch just to speed things up. Inference mode just means we want to use our model in inference mode. And then we can go outputs equals our model. And I'm going to use this double star syntax, which means you might see this in a few places online. Means input all of the dictionary keys as named arguments. Arguments/parameters. So that just means it's going to put in input IDs and attention mask as if they were parameters. These lines of code here do the same thing. Model input IDs equals our inputs, input IDs, and then we go attention mask equals inputs, attention mask. So both of these will return the same thing. Outputs verbose Let's just test if this is true, actually. We have outputs. Let's see what we get. And then we have outputs verbose. See, that prediction was very quick still, right? Beautiful. And do these equal each other? Inputs, outputs verbose equals outputs. Boolean value of more than one value is ambiguous. Okay, that's right. We can just see that they're visually the same, right? Wonderful. Now, what can we do? Now, these are logits. So logits, the raw output of a model, referred to as logits. Let's convert this into convert logits to prediction probability plus label. So we want predicted class ID. We actually don't need to go, we can get the class ID by just taking the max of this. Remember, the max of the logits is the particular index that our model is predicting as the most likely output, not the corrected output, just the most likely output based on its training data. So we'll take the outputs, we'll index into the logits, and we'll take the argmax, so the max index here, and we'll take the item, so it's no longer a tensor. So let's see if this makes sense. Predicted class ID, what do we get from that? 1. Beautiful. The first index, that's what's predicted. So that is, what was our sentence? A delicious photo of a plate of bacon, of scrambled eggs, toast, and bacon. That means that it's predicting as food. Exactly what we wanted, right? And then we're going to go prediction probability equals torch softmax on the logits. So we can go outputs.logits, and then the dimension is going to be the first dimension. So this dimension here, that bracket there, instead of this 0 dimension on the outside. So 0, 1. And then we're going to get the max value of that item. Let's check the prediction probability. What do we get from that? 0.999, so it's very confident there. And now we've got everything we need to do a nice little printout here. So text is going to be our sample text food. Print, we'll do our predicted label. Oh, here's where we'll have to. We can go model. So our model here, we've set up there. And because we've downloaded it from Hugging Face, we get a config. Yeah, there we go. Is this going to be in our file over here? Config JSON, there we go. That's what we want. Boom, ID to label, that's what we want, and label to ID. So we can use this. This is when we set these many videos ago and uploaded our model. We now get a config. This is why we put our model on Hugging Face, because we get all this helpful information stored with our model. So to get this, we can get our ID to label. Beautiful, that's what we want. So we want to take our model config, ID to label, and then we want to pass it the predicted class ID. So this one here, and then we're going to go print, and then we're going to put out the prediction probability. Is that going to be prediction probability? What do we get? Sample text food is not defined. Is that a typo? Of course it is. Sample food text. Wonderful. Now, what do we get from food, not food classifier on sample food text? Do we get the same thing here? Wonderful. The exact same output. Food with a score of that. So that's how we can do our predictions with raw PyTorch. But of course, the pipeline just abstracts a few steps away and does these processing steps for us. So we have covered an exceptional amount of ground to go from a data set to a trained, reusable model that we can now use to make predictions on custom data. So we could send this model to someone and they could put it in an application, or they could use it to filter a really large data set of 700 million images for food images. Like if the image caption is food, we want to save that to a database, then we can use that for Nutrify, so we can perform data analysis on food images. You could use this for retrain your own model for a whole bunch of different things. If you're an insurance company, you could test if the claim was someone at fault versus not at fault. So I think we've covered a fair few steps. I think in the next video, which may be an optional one, but If you want to, we're going to go through everything in one step. So putting it all together, because right now that we've got all of our code is kind of all over the place. So what if we wanted to go from a data set to a trained model on Hugging Face in one notebook cell? You think you can do that? That's going to be my challenge to you to try out for the next video, is to condense everything we've done into one single cell. Give that a shot, and I'll see you in the next video. We'll put everything we've done so far together before we go on to building a demo. I'll see you there. We've made an incredible amount of progress so far working on our text classification problem. We've now got a trained model on the Hugging Face hub, all the way from getting a dataset, pre-processing it, building the model, training the model, and evaluating it. Now let's put it all together in an end-to-end coding cell so we can see everything in unison. So let's go end-to-end from data import to model building to model evaluation to model saving. Beautiful. We'll put our workflow, we'll go right from here, end up to here. And then later on, we'll build a shareable demo. But this is what we're focused on, these first 7 steps, 0, 1, 2, 3, 4, 5, 6. So let's do a little outline. It's nothing that we can't handle. So 1, we'll write the outline first, and then we'll go through putting code on each part of it. Actually, model saving for our text classification project. Beautiful. So just so we know what we're working on. Number 2 is going to be set up variables for model training and saving pipeline. Number 3 is going to be create a directory for saving models. Number 4 is load and pre-process the dataset from Hugging Face Hub. Number 5 is going to be import a tokenizer and map it to our dataset. Then what should we do? Well, we need to evaluate our model. So number 6 can be set up an evaluation metric. Number 7, we'll set up a model. And then number 8 we'll train the model. Number 9 can be save the trained model to a local directory. Number 10 can be push the model to the Hugging Face hub. And then number 11 can be evaluate the model on the test data. Woohoo! Look at that. Now we've got a fair bit of code to write, but we can do it together. So let's have a look over here. This is basically just taking our outline here and turning it into a single code cell. So we'd ideally like this to be able to run if we just copied all of this code later on and copied it into a completely new notebook. So that's why we're going to start by importing the libraries that we need, pretrained to print out some results. We're going to import path from pathlib to create a file or a folder. We'll get NumPy, of course. We'll import Torch, import Hugging Face Datasets, import Evaluate, and then from transformers, we'll get all of our transformers related packages and modules. So from transformers, we need pipeline. Oh, I've got a typo there. From transformers, import TrainingArguments and trainer. And then from transformers, I'm going to import auto tokenizer and auto model for sequence classification. Beautiful. So step 1, done, importing the necessary packages. Now we just have to put them together. So we'll set up our dataset name. This is going to be Mr. D. Burke. We come over here. If we go to my profile, I've got the link. Here we go. Learn HF, food, not food, image captions. I'm just going to copy that. And if we pass it into these inverted commas, wonderful. Then we'll create the model name. This is going to be the original model that we want to download from Hugging Face, which is in our case, Distilbert. Distilbert based uncased. Wonderful. And let's create a save directory name, which will be models, the same name we've been using throughout. Models, learn HF, food, not food, text classifier. And then I'll put Distilbert base uncased on the end there. Wonderful. Does that look correct? Yes, it does. Now let's create a directory. So we will go print. I want to print out some info as we're going along. So as we start to go through each of these steps, let's make little milestone printouts, shall we? So creating directory for saving models. And then we'll put model save dir name. Wonderful. And then model save dir will equal path model save dir name. And then we can go model save dir mk dir. And then we'll go parents equals true. And then exist OK equals true. Now let's just run that. There we go, making directory. We should already have one of those over here. Models, there we go. Our models already still exist. And if we really wanted to test this, we could actually delete this runtime and just start running this from scratch. We might try that towards the end. So, and if I forget, well, that's a bit of extra curriculum for you. So we have info. Let's load and pre-process the dataset. First thing we have to do, print out a little statement. So we'll do downloading dataset from Hugging Face Hub. The name will, of course, be the name that we set above. So will be the dataset name. And then we can set it up by going dataset equals datasets, load dataset, and we'll load our dataset name. Beautiful. And then we're going to import our tokenizer and map it to our dataset, because remember, once we download this dataset, it'll just be the raw text data. So we need to process it. But before we do, let's map ID to label, because remember our dataset comes in. We need to turn these labels into numeric values. So we're going to map ID to label and label to ID. We'll create those dictionary mappings. So let's go 0 is going to be not food. We'll create these manually. You could do them programmatically as we've done throughout the notebook. I'll leave that up to you to decide how you'd like to do. For now, I'm just going to put that here as not food, and then 0, and then food as 1. Beautiful. And then now we can create a function to map IDs to labels in the dataset. And then we'll go def map labels to number, and then example. And then we'll go example label is going to equal label to ID. And then we'll put in here example label. Wonderful. Return example. And we can map our pre-processing function to our dataset. So dataset equals dataset. Train is going to be our only split here, because we haven't split it into train and test yet. We'll do that in a moment. We're going to map our map labels to number function, and then we can create our splits. So split the data set into train test sets. We'll go data set equals, this will give us two splits. One, a test size of 20% of the entire data. And I'm going to use a seed of 42 so that our splits are the same as before. And then if we do that, we should have a downloaded data set. Created directory, yes we do, yes we do. And then if we have a look at our data set let's look at the first example. That should have a numeric label of 0, set of headphones placed on a desk. Wonderful. We're making some good progress here. So we've got our data set. We've turned the labels into numeric value. Now we need to turn the text into numeric values. And to do that, we can use a tokenizer. So let's write an info statement here because we're up to the next milestone. Info, just going to X out of that. Info, we're going to put tokenizing text for model training with tokenizer. And the tokenizer is, of course, going to be paired with our model name. So this is Distilbert. Wonderful. And we'll go tokenizer equals auto tokenizer from pre-trained. And the pre-trained model name or path is going to equal model name. And then we want to use fast equals true. So use fast, we'll use the fast version of the tokenizer. I'm pretty sure this is true by default. So we'll get that downloaded. And then we want to, just like we created a function to turn our labels into numbers, we'll do the same thing to turn our text into numbers or tokenize our text. So create function to tokenize text samples. So def tokenize text examples. Oh, we'll just write here, turn text into numbers. And what do we have to do here? Well, here's where we return our tokenizer. So what we've created here, and we want to turn the examples text column into numbers, and we're going to use padding so that we make sure each batch has the same length sample, and then we'll use truncation. I don't think we have any samples that are over our model's max size of 512, and we can figure out the model's max size by going into, if we look up Distilbert, we've seen this before, but if we look in the config.json, we have the max size is 512 there. So we don't have any samples because our samples are relatively small. We don't have any samples that are over 512 tokens in length. Now, let's keep pushing forward. We've got this. Tokenized dataset is going to be what? We have to pre-process our dataset. So dataset.map. We're going to map the function that we just created, tokenize text. We're going to set batch to equal to true because when we're tokenizing, we want to do as many samples as possible. And we're going to set the batch size, in batches that is, as possible, batch size to 1,000. And so we should now have a tokenized dataset. So tokenized dataset, let's see what that looks like. It's going to download the dataset. There we go, mapping function. That works nice and quick. There we go, there's our dataset. I'm going to put this in front. We should have a numeric version now. Tokenized dataset. Beautiful. That's exactly what we want. Input IDs, text. Okay, we're making good progress. Now, we've got a tokenized dataset. We have labels in numbers. We have data in numbers. We need a way to evaluate how our model performs. So we're going to create an accuracy metric. And we can do that with evaluate.loadAccuracy. And then we can make a function, compute accuracy, and we'll put in the predictions and labels. This is what our model is going to return. So we'll separate these, predictions, labels equals predictions and labels. And then we'll do a check here, the len of predictions.shape. We do this because I'm just going to write here, model will output logits in the form, it's going to be a tuple of item n, depending on number of classes you have. But we want to compare labels which are in the format 00001. Oh, sorry, not in that format completely, are they? Yeah. So this is going to be, this is going to be nested. Item N, and this can be item M, item M, right? Depending on the number of classes you have. So, but we want to format this. So we want to take this and turn it into the maximum value that is in here, the index that's the maximum value. So if we had 3 classes, or item 1, 2, 3, we want the maximum of this. So if item 3 is the max, we want index 0, 1, 2 to compare to our labels. We want our labels and predictions to be in the same shape. So I'm just going to move this over to here. And then we want, if our prediction shape is greater or equal than 2, we want to reduce it in size by taking the NP argmax of the predictions on the first axis. So that's going to reduce this to a single value. Let me just show you what that looks like, because that can be a little bit confusing. So if we have NP array and we have 0, 1, 2, and then if we do NP argmax on this, what do we get? 2. So the maximum value is here. We want to reduce this in size to be a single dimension. So that's what we're doing there. Do we import NumPy? Import NumPy as NumPy. Yep, we did. NP. And then we can go return accuracy metric, compute predictions equals predictions, and then references equals our labels. So this takes in predictions and labels, separates them into their own variables, sorts it out or figures out if the predictions are, oh, excuse me, that's why that didn't work. If the predictions are over a certain shape, we reduce them in size to get the NP argmax, and then we compare the predictions to the labels, the ground truth labels. So what's next? We should set up a model. Oh, we're making some progress here. Okay, so let's print out a little milestone here so we know what we're doing. So info loading model is going to be model name. And so we can create our model using model equals auto model for sequence classification, because we're working with text classification. We want to classify image captions into food or not food. And of course, this would be, the workflow would be very similar even if you're working on another type of data set for text classification. So we get this from up here. From transformers, import auto model for sequence classification. And then we have, how many labels do we have? We have 2, because we're working with classes that are food, not food. So if we go back, so food, not food, we have 2 labels. In your data set, you may have more than that. So just keep that in mind. We could probably programmatically do this, depending on how many unique labels we had in our data set. So that's something to keep in mind for later on. But if we go ID to label is going to be ID to label. Label to ID is going to be label to ID. This comes from back up the top, which is our dictionary mappings. I'll write here, create mapping from label to ID and ID to label. So we can go in and out of numeric and non-numeric. There is our model. Wonderful. This is how powerful the Transformers library is, right? Or the Hugging Face ecosystem is. We're in about 80 lines of code with plenty of comments. We're going from custom dataset to custom trained model. We're not finished yet though. Model loading complete. That's always a fun step. Are we working? Is this working? Tokenizing text, yes we have. We're loading model. It's saying that we should probably train that. Well, hey, I agree. But not just yet. We need to set up our training arguments. So set up training arguments. These are hyperparameters for our model. So recall hyperparameters are settings that we can set. So hyperparameters equals settings that we can set as developers. And then parameters equals settings / weights our model learns on its own. So we can set up our training args by going training arguments, and then there is a whole bunch of things that we can pass in here. So if we go transformers, training arguments, oh my goodness, a bunch of typos, but luckily Google has some great searching, training arguments. We don't have to use all of these. And in fact, I would say as extracurriculum, it is your practice to go through and read all of these at least twice. So even if you don't understand them at first, I don't understand them all, reading them over them will help you learn more and more. And there's a whole bunch of different extra resources like that the Hugging Face team link to learn more. We're just going to use a handful of the settings for training arguments that are most relevant to our project. If you were training a much larger scale model, you probably want to pay more attention to these. In our case, our model isn't a huge, large model, but it does work for a very specific task. So we want to set up the output directory. We want to set up the learning rate to 0001. That's a very experimental value. So if you find your model isn't doing too well, try tweaking the learning rate up and down. Equals 32. And then we go per device eval batch size equals 32 as well. And then we're going to go for the training epochs. We'll set it to a number of 10. We want to eval or evaluate our model on the evaluation dataset every epoch. And we want to save our model. Remember that an epoch is one lap of the data. The neighbor's dog is having an absolute field day with all the new people that are over. So if you can hear the dog in the background, let's just treat it as encouragement for us to keep going and build everything in one cell, okay? We got this. We're going to set the total of saving to 3, because if we're saving every epoch, we're doing 10 epochs, we don't need 10 replicas of our model. We're going to load the best model at the end anyway, and use CPU false. That means the trainer is going to, we haven't set it up just yet, is going to use the best accelerator that we have available. In our case on Google Colab, it will be a GPU, but if you're working locally, it will hopefully be a GPU as well. And then we go seed equals 42, and then load best model at end. This is a really helpful one. We'll set that to true. The logging strategy, how often do we want our training regime to output information to the output here, standard out. And then we'll go report to. We don't want to use any external tracking system. We can if we wanted to. That's just something I'll leave you dig into. And then push to hub. We're not going to set that to true just yet because we're going to set that later on. Down here, push the model to Hugging Face hub. And then we can go hub private repo equals false. So note, this will make our model public by default. So keep that in mind that if you're training models and they're not supposed to be public, make sure you set it to private, because otherwise other people will be able to access your model from the Hugging Face hub and use it. So now we've got the third part in our training arc, which is setting up trainer. We've set up the training arguments. Now we set up trainer. So let's do that. So we'll create the trainer instance, and that is trainer equals trainer and model equals model. Then we're going to go args equals training args. And then we'll set up the train data set equals tokenized data set, train, and then the eval data set equals tokenized data set test. We'll evaluate on the test data set. We'll set the tokenizer equal to our tokenizer from above. And then the compute metrics will set in our calculate or our compute accuracy. Better yet, compute accuracy function. Woohoo, wonderful. So we should now have an instance of trainer. Let's see how this goes. Creating directory, downloading dataset, loading model, and we have a loaded model and we have a trainer. Wonderful. Now I can just tell there's probably a typo somewhere, but it looks pretty good for now. Okay, fingers crossed. We won't count our chickens before we have a trained model though. So commencing model training. All right, and now we're going to set our results equal to trainer.train. That'll train a model. and then when we can save it to a local directory. So this is another milestone. I'm going to print out model training complete, and we'll go saving model to local path, and this will be the model save dir. We're doing all this printing out so that if we were to run this in a script, we'd get some cool things in our console, right? And then we can go trainer.save model output dir equals model save dir. And then once we've saved it there, we can push it to the Hugging Face hub. So let's do that. Print info, and we'll go uploading model to Hugging Face hub, ... and we'll go model upload URL. We can upload our model with what? We can upload it with trainer.push to hub, and we can set a commit message. This is going to appear in our Hugging Face hub model repo. So if we come over to here, oh, that's our demo. There's a model there. Commit message is going to appear here. There we go, uploading food not food text classifier model. And we'll put in one here. Uploading food not food text classifier model, and then we'll go putting it all together because we're doing all this in one cell, right? And then if you wanted to, you can put your token here. I would advise not to, but that's just an opportunity. Your token here. See, mine is going to, of course, read the token from over there, Hugging Face token. It's going to read that from behind the scenes. So just make sure you've gone through the setup step for that to work. That's at learnhuggingface.com/extras/setup. So there we go. You can set up your token if you're using Google Colab. Start here, Google Colab, and set up your token by following those steps. But that's going to upload to the Hugging Face hub. Let's print out an info statement to make sure that that works. We are one step away. Model upload complete. Model available at model. We'll get our upload URL printed out. Upload URL. And then, of course, we need to evaluate our model. So let's see how our model does on the evaluation data or the test data. So info, performing evaluation on test dataset, ... And then how do we perform our evaluation? We create some predictions because evaluation is comparing predictions from the model to truth labels. So trainer.predict, and then we can call tokenized dataset on our test version of the dataset. So this is data our model hadn't seen during training. Prediction values is going to be predictions all.predictions. And then prediction metrics is going to be predictions all.metrics. So we can have a look at both of those if we wanted to. And then we can print out the results that our model got on the test data set. So info prediction metrics on the test data is going to be, this is where our pretty print statement comes right at the end. Let's see if this all works. Prediction metrics. Whew. We'll run that code. A fair bit of code, but we've done it. 136 lines to go end to end from loading a data set to training a model. How cool is this? I'll never get tired of seeing this. Our model training performing incredibly well on our small data set for a targeted problem. And of course, we could add more data to it to improve it. That's actually a big extension you could try, is to add more data since we're only using 250 samples. The benefit of that is that training happens really quickly. Model training complete, saving model to local path. It's saved there. Now it's going to upload it to the Hugging Face hub. Oh, yes. So keep attention over here. Let's see if this changes. And there we go. Oh, performing evaluation on the test data set, and the metrics that we get are incredible. Accuracy of 100%, a really low test loss value. Test samples are really quick. And do we get an updated commit message, which should be uploading food, not food, text classifier model, putting it all together. If I refresh this on my page, there we go. We get putting it all together. So if we wanted to create a pipeline where we continually improve our model over time, we could continue to update it or upload it to the Hugging Face Hub and just keep uploading it here, and we'd have different versions of it. How cool is that? Now, of course, there's going to be one more step that I didn't include there, which is number 12 is make sure the model works by testing it on a custom sample. So let's go food, not food classifier. How do we do this? Well, we import our pipeline from transformers, import pipeline, which of course we've already done above. I'm just putting it here again to show you. Task is going to be text classification. We've now got our own custom model hosted on the Hugging Face Hub. So we can use this one here, this model, of course, change out your username, my username, sorry, for your username. And then we can go model equals model saved. This is going to load it from local, but we could also load it from this path. And then we can put the device here, which is, I'll set mine, just hard code it to CUDA, which is going to be NVIDIA GPU, if it's available, that is. If Torch CUDA is available, which I kind of know it is, but we'll do it anyway, else torch.device. We'll run it on CPU if the GPU is not available. Then we can return the top K, the top number 1 sample. We'll set the batch size to 32 so we can do batch predictions if we wanted to. And I've pressed the down arrow too many times. And let's call our food not food classifier. This is so exciting. Yo! We just trained a food not food text classifier in 150 lines of code in a single Google Colab cell. Well, 2 cells, to be fair. There we go. It's food. Wow. Food not food classifier. Now, what if we tried it again on something interesting? So our model, a food not food, because it's got that. So what if we take out food not food, a text classifier? Oh, excuse me. I think the mere presence of the word food is causing our model to think that it's food, which would make sense. Not food. Wow. So there's something to think about, is whether the food not food is getting a bit meta here. If there's food not food in our text classifier model, it predicts that it's food, but really this sentence is not about food, is it? So something to think about is if we wanted to expand our data set with better samples so that our model, if it saw samples like this, would know that it's not about food. But, big round of applause. You can go for a walk, and I'm going to go for a walk after that because that was quite intense. But what we did just there was we put it all together. We imported the necessary packages. We set up variables for model training and saving, created a directory, loaded and pre-processed a data set. We imported, we turned the labels into numbers. We imported a tokenizer to turn the text into numbers. We set up an evaluation metric because evaluating a model is as important as training a model. We set up a model from the Hugging Face Hub. So this is a non-trained model, a DistillBERT model. We set up our training arguments. Excuse me, this should be training arguments. Hyperparameters. We created an instance of the Hugging Face trainer, which uses PyTorch behind the scenes to train a model. We trained our model, saved it to a local directory, pushed it to Hugging Face Hub, as you can see here. Of course, that'll be on your username if you've set that up. And then we have a upload URL. We evaluated the model on our test data. We saw that it performed incredibly well. Then we loaded that model into a pipeline, predicted on 2 custom samples, and it looks like our model is doing quite well, even on custom samples. And we have some next steps if we wanted to improve our model. We've got some data insight now because we've tried it on custom samples. So we've seen that for some samples, it doesn't perform as well as we'd like. So potentially we could expand our data set. Phew. Now I think there's one more big step to go of our text classification project, and that is turning it into a demo, a shareable demo. So it's not just lines of code in a notebook anymore. It's an application. It's this. So it's like, yo, we've got one more step to go, and that's building a demo. So if you're ready, put your hand up, and over the next few videos, we'll get a demo like this running on your own Hugging Face account. So I'll see you there.
You've officially built, trained, and ran inference on a custom model. Most people talk about AI, but you're actually building it. But if you stop here, your model is just code sitting in a notebook. In the full Zero to Mastery Hugging Face Bootcamp course, you'll take this exact project to the finish line. Dan will help you turn this model into a live demo using Gradio and Hugging Face Spaces so that you can share your work with the world and add it to your professional portfolio. And this is just the beginning. From there, you'll go into a second project, a massive end-to-end custom object detection project where you'll teach a computer to see and identify objects in real time. You can get all of this by joining the Zero to Mastery Academy. That means you get access to the full Hugging Face Bootcamp and every other ZTM course, plus priority support from our instructors and our world-class mentors inside our private community. If you enjoyed this crash course, please drop it a like and leave a comment. It really helps us reach people just like you. Alright, thanks for watching, and I hope to see you inside the Zero to Mastery Academy.